Και πού θα το βάλουμε?
Θα το βάλει στην άκρη για να κάθεται εδώ πέρα να το κοιτάει, στο πλάι του.
Στις παρουσιάσεις όρθιοι θα είμαστε.
Αυτό λέω, τις ξέρετε τι είναι το περιεχόμενο.
Όχι, υπάρχει το clicker, αυτό δεν είναι.
Και εδώ να είναι, εντάξει, η φωτογραφία μπορεί να βγει.
Άμα είναι όρθιος ο άνθρωπος, ναι. Άμα κάθεται ο καθένας σας, δεν θα βγει. Γιατί θα αρχίσει το μισό υπολογιστή εδώ πέρα και μετά θα είναι κεφάλι.
Εδώ θα σας ακούνε, γιατί εμείς τριμάρουμε στο site του Πολυτεχνείου, δεν θα ακούγεστε. Άρα πρέπει να έχετε αυτό μαζί.
Α, είναι online.
Ναι, είναι διαδικτυακά γι' αυτό.
Ξεκινάμε, γιατί έρχεται ο κύριος Πρίτας.
Εντάξει, οκ.
Αυτό είναι ξεκινάμε. Άμα υποτίθεται σας ακούμε διαδικτυακά. Οπότε πρέπει να έχουμε τουλάχιστον αυτό το οποίο γιατί είναι.
Δεν έχει μεγαλύτερο. Έχει καλώδιο.
Έχω. Δεν είναι το chip. Απλά το άλλο είναι για το. Αυτό είναι το ίντερνετ και αυτό είναι το χώρο.
Και το power bank το χρειάζεστε εδώ πέρα πάνω πλέον.
Yes, hello. Καθίστε, Ελένη. Πάει. Ναι, καθίστε, ξεκινάμε. Καθίστε. Όχι, κάτσε. Hello. Hello. Can we start? Dear colleagues, dear friends, it's a great pleasure to welcome you all at the National Technical University of Athens and to our Zografou campus for this joint workshop on infrastructure, energy sustainability in climate changing. We're especially honored to host our distinguished colleagues from Columbia University and grateful for the opportunity to continue building bridges between our institutes across the Atlantic. Bridges grounded in mutual respect, shared scientific values, and the commitment to addressing some of the most pressing challenges of our time. Both Greece and the United States of America, like much of the world, are increasingly affected by extreme weather events, environmental degradation, and the long-term impacts of climate change. The resilience of our cities, infrastructure, and energy systems is no longer a distant concern. It is an urgent scientific and societal priority. This two-day workshop brings together researchers from diverse fields: engineering, climate science, sustainability, artificial intelligence, and public policy to share insights, present cutting-edge research, and lay the ground for future collaboration. Our objective is not only to present what we are currently working on, but to explore how we might work together in the years ahead. Today, we will hear presentations that reflect the depth and breadth of expertise of both Columbia University and NTUA, from smart cities and automated mobility to digital tools for climate adaptation and infrastructure resilience. Tomorrow, we will focus on discussion, dialogue and planning, identifying areas where our complementarity strengths can lead to impactful joint research initiatives. I would like to thank all of you for being here together, and especially thanks the organizing team of both institutions, including George Odatis, Ioannis Kimissis, and many others for their dedication and support in making this event possible. Let us make the most of this opportunity to learn from each other, to question, to connect and create the foundations for meaningful transatlantic cooperation. welcome you all again to NTUA. I wish all a productive and inspiring workshop. Thank you very much.
Hello everyone, I'm George Diodadis. I'm a professor of civil engineering and engineering mechanics at Columbia University, and I also have a joint appointment with the Department of Earth and Environmental Engineering, and currently I'm serving as the Vice Dean for Research for the School of Engineering and Applied Science. First of all, I would like to thank the National Technical University of Athens for organizing this workshop. This workshop was inspired by a visit of the rector, Professor Yannis Hadjigeorgiou, a few months ago at Columbia, and there the two universities decided that this is the right time to establish a close collaboration on research. And the best way is to bring together faculty from both institutions, make presentations of their work, and then talk to find common areas of interest. And we are starting with the effects of climate change on energy and the infrastructure, but this is the first in a series of workshops. There are many other areas of potential research collaboration between our two institutions, and very soon others will follow. But we decided to start from this topic because it is a topic of critical importance both for Greece and the United States. For me, it is especially important coming back to my alma mater. I graduated from the National Technical University of Athens in 1982 from the Department of Civil Engineering, and Professor Theodosios Tasios was my thesis advisor. So coming back is very important for me. Although I took most of my classes at the Patission campus, from the Zografou campus I only took the surveying exercises. Back then, as you know, pretty much the entire university was still based in the Patission campus. So thank you very, very much for organizing this. As far as Columbia is concerned, the participants are the School of Engineering and Applied Science, of course, but Columbia's Athens Global Center is one of the contributors and organizers of this event, and I would like to ask its director, Stefanos Gandolfo, to say a few words. Stefanos?
Thank you, George. Good afternoon, everyone. I'm Stefanos Gandolfo. I'm the director of the Columbia Global Center here in Athens, which is part of Columbia's network of 10 global centers around the world. We're the newest one. We started exactly a year ago today, so I think it's very, it's a good omen that we're here celebrating our 1-year anniversary with all of you. What is the Columbia Global Center? Just very quickly, we are here to help collaborations which are already existing and blossoming, as the one between NTUA and engineering at Columbia. And we want to build and help in all the ways that we can in helping these collaborations grow and develop even further. And in fact, with Banos Varvarigos and several other faculty here at NTUA, we have been working on several of collaborations, which I think very soon we will be able to announce and share with you more broadly. We're also here to help be a convening space in order to exchange ideas and to learn from each other. So these kinds of workshops, I think, are absolutely critical in our mission in trying to help and establish this bridge of communication. And the third thing is that we're trying to facilitate the exchange of students from Colombia to Greece, but also from Greece to Colombia. And we do this by having master's and undergraduate, graduate and undergraduate students from all different kinds of schools from Colombia come to Greece, but also through various ways, also helping Greek students go to Colombia. We have a very broad range of issues that we cover, from classical antiquity. No one can do anything in Greece without mentioning the ancient world. But of course, we're focusing a lot on engineering, innovation, entrepreneurship, climate change, migration, and some other global challenges. So I don't want to take any more of the precious time that we have today, and I look forward to today's presentations. Thank you.
Let me say some things also. I'm Manos Varvarigos. I'm a professor of electrical and computer engineering, and I'm the vice rector of research, innovation and extroversion. We're very happy to have our colleagues from Columbia University. I think we have very natural bonds with Columbia University, in the sense that a lot of our graduates have gone to for further studies to Columbia. Some of them are professors, and vice versa. A lot of some professors here have graduated from Columbia. It happens, by the way, just by accident, that tomorrow Professor Giannakakis from Columbia is going to get an honorary degree from electrical engineering department here. So this is just by accident. I think we have a lot of bonds which are natural, but of course, it is good also to organize things so that these bonds become deeper. So we are organizing things that are relate to the joint master's degrees in several areas. That we already have some, but we want to make them more appealing. We organize things with the business school of Columbia. At the Global Columbia Center, as Stefano said before. But of course, both universities are more interested in research, and that's why we have this research day, where we want to share some problems. Some professors from NTUA, some professors from Columbia talk about their research work. It's a small area, sustainability, relatively narrow, but one has to start from somewhere. And the idea is that professors from either side will get more familiar with the work of each other, and then find common problems, and then these individual relationships can grow, and so that we have something bigger. So let's start with the program. And I would like to ask okay, we have alternating presentations from Columbia University and from NTUA. Professor Adam Sobel is first.
Did we ever get the slides to work? That's it? Yeah.
Up, down. Okay. No. Up, down.
Okay. But we don't see it here, so you're going to switch it. Oh, okay. Great. I'm going to put my time. Thanks so much to the organizers. It's a pleasure to be here in Athens. Yeah, my name is Adam Sobel. I'm an atmospheric scientist. I study climate and weather. And I'm going to explain what the title means in the talk. So a question I started to ask myself in the last 10 years is how can physical climate science, that's the science we do to understand how the climate works, support action? It's not something, as opposed to just understanding the system, how can we help decision making? So I'm talking about something we call climate risk science, and what that means is science that makes impacts concrete and quantitative for decision making. And the word risk is because we have to quantify the probabilities of extreme events. So this is a kind of challenge beyond normal climate science. Climate science is normally about averages. Climate is about averages, but now we want to know the extreme events of the tails of the distribution. That's harder. And this, what I'm talking about here, is mostly relevant to adaptation. In other words, doing things to deal with the climate change that's happening, as opposed to stopping it, which is mitigation, which is very important, but depends on different science, I would argue. So this is relevant to a bunch of things, and I put some stories from the US media. It's relevant to insurance. That's how I learned how I got started in this area, is working with companies in the insurance industry. Risk disclosure, and we have big problems with the insurance industry that are going to affect the housing market and the economy in the United States, because we keep having a lot of disasters and the insurance system is breaking. I don't want to go into details on that, but it's a problem. Risk disclosure, so this is not happening in the US under the new administration, but it's still happening in Europe, that companies have to disclose their climate risk as part of financial disclosure. And to disclose it, you have to first know what it is, and that's not so easy to do. And adaptation planning. So, for example, there had been the possibility of building storm barriers around New York after a very bad storm that we had 13 years ago. George Diadatis can tell you a lot about that. But these are all kinds of things that we use the science I'm talking about for. But I'm going to talk about the science itself. So when we talk about risk, we can decompose it as having three components: hazard, vulnerability, and exposure. So hazard means the geophysical part. If it's a storm, it means how strong does the wind get? How high does the flooding get? Some physical variable that takes on an extreme value. The exposure is whatever you're worried about losing. Could be buildings, could be human well-being, could be anything. But let's imagine it's buildings for the sake of argument. And vulnerability tells us how much of the building will be lost, how much value will be lost if the flooding gets this high or the wind gets this strong. So I'll come back to the details on this. But you know all these things. You can calculate a loss from a given event, geophysical event like a storm. And all the examples I'm going to talk about today are about hurricanes, just storms, tropical cyclone, we say. So if you can calculate that for one event, then if you have a lot of events, you can calculate statistics. What's the probability of a loss of a given magnitude? How often will you see a loss of this much? And then adaptation is the process of trying to reduce that risk, usually by changing the vulnerability or exposure. Okay, and a theme I'll come back to is that the science of doing this is done very differently in different applications. So the insurance people do it differently than the economists do it different than people in agriculture and engineering. And I think we could have a bit more of a systematic field, but I'll come back to that at the end. So if you want to know the hazard, most of my science is about the hazard because I'm a meteorologist, so I study storms and weather and climate. And so if you want to know, let's say you want to know the probability of a hurricane of a certain magnitude in New York. But the magnitude is so high that it has not happened in the last 150 years, so we don't have any data. A category 3 hurricane, let's say. So you can go to the historical record. How do you know then the probability of this event? You can go to the historical record, which is great because it's real observations and you believe it. But on the other hand, it doesn't capture everything that's possible. So the category 3 hurricane, if it has not happened in the last 150 years, you would calculate a probability of 0. But the probability is probably not 0. It's just we haven't waited long enough to see it happen. Also, even the historical data is not representative of the future anymore because the climate is changing. So we use climate models in my field a lot. These are complicated physical models. Now there's AI ones too, but let's talk about the physical models. They can simulate climate and weather and everything all together. But the problem is they're not so good at extreme events. They don't have very good hurricanes, for example. They have systematic errors. I mean, they're quite good actually, but there's some things that are persistently not quite right, and that causes problems. And they don't represent impacts at all. They're just models of the Earth system, not human systems. In the insurance industry, they use something called catastrophe models. These are empirical models that they're trying to solve the problem that the history is too short. So they take the historical record and they make more events that look like the ones in the historical record using some kind of Monte Carlo thing. So they expand the history. So if you want to know the 1 in 1,000-year storm, you make 1,000 years of storms that aren't real, but you hope they're realistic. So that's very good, but they're empirical. They're only starting to do climate change. You need some physics to do climate change. You can't just use past data. They tend to be for specific countries, so they're only very good in the markets where there's a lot of insurance. And a lot of them are proprietary, so we don't really know what's in them, and you can't compare them, and it's hard to understand how good they really are from the outside. So in our work, we are doing work that's motivated by insurance, but trying to be open source and a little more public-facing and incorporate climate change. So we built our own hurricane model, Columbia Tropical Cyclone Hazard Model. This is my colleague, Jiaying Li, who is the main person that built it, with some help from a few other colleagues. So it's a model where we take, let's see, one of these is, this. So we take a climate simulation that gives us a simulation of the future climate, or the present climate, or past climate, could be anything, but we don't believe the hurricanes. Ooh, what did I do? I don't know. But we don't believe the hurricanes in that simulation, so we generate our own hurricanes. Our model takes the environmental information, takes the large-scale climate information from the parent climate model and generates hurricanes that are consistent with that. So I'm not going to really explain how it works. It's sort of a statistical model, but it has some physical information in it. So we assume that in the future, the relationship between climate and hurricanes is the same, but the climate itself can change. It's represented by a few physical variables at each point in space and time. So we generate lots of hurricanes, and we can generate them for whatever scenario we want, including the future, and we can estimate hazard and risk. So when we started doing this, we wrote the first papers I ever wrote that were about specific cities and states. So I'm not going to talk about these results in detail, but this is a typical kind of thing we look at. So these are return period curves. On the return period is the inverse of the frequency of the event. So it's how many years on average you would have to wait before an event of this magnitude occurs. So on the y-axis is wind speed. So in Mumbai or in New York, in India or in New York State where we live, you know, how long would you have to wait? This is a log scale of the return period in years. So the 100-year event is, you know, this many, 110 something knots. We use knots, which is half a meter per second, etc. So this is the kind of result we are doing. Probabilities of extreme events of a given magnitude. That's what we're characterizing. And the point of the model, the black curves are what you estimate from the observations. But the observations, you can only go out to return periods as large as how much data you have. So if you have 100 years of data, you can go to not quite 100 years. So the point of our modeling work is that we can make the curve go out further to estimate these very big events that have very low probabilities, or very large return periods. Okay, so that's the kind of work we are doing. And when we do climate change, so that's the whole point of this model, part of the point of it anyway, is that we can do climate change. The results I just showed you were for the past climate. This is the first climate change study we did with our model. I need to see the screen here so I can see what I'm showing you. This is a simulation of a particular climate scenario with time on the x-axis. So we take it from a lot of climate models. What am I doing? Oops. Sorry. I'm trying to learn how to use it. So here's time going forward, and this is the number of hurricanes on the Earth. Number as a function of time. And the black is the observations. So our model is the shading, and you can see it agrees with the observations in the past. That's because we tuned it to do that. It's an empirical model. But in the future, there's two branches. Some solutions go up and some go down. So we have some simulations that give us more hurricanes in the future and some that give us fewer hurricanes in the future. And the reason for that is not because we're downscaling many climate models. We call this downscaling, making new hurricanes inside the climate model. It's because we have two versions of our model that represent the climate slightly differently. There's a variable that's the humidity, the amount of moisture in the air, and there's two different ways of measuring, of representing it. The relative humidity, or something called the saturation deficit. Both are comparing the actual amount of moisture to the maximum possible before you reach saturation. But one is dividing the two numbers and one is subtracting them. And depending which you use, it gives the same answer in the past, but totally different answers in the future. And we don't know which one is right. And generally, we don't know it's a fundamental scientific uncertainty. We don't know actually why there's about 80 or 90 storms per year in the past climate. We don't have a good theory for the number of storms. So this is why we can't constrain the model better in the future. So this is a real problem. If we can't even tell you if the future will have more hurricanes or fewer hurricanes. You know, we know it's warmer, but this is a problem. So when we go to, so I'm going to come back to that problem because it's sort of a deep scientific uncertainty. But before doing that, I want to talk a little bit about going from hazard to risk. So I talked about exposure and vulnerability. So in our work, we are meteorologists. We only started in our research to learn about actually modeling damage, exposure and vulnerability to get lost. So this is the first thing we did. This is a study with an insurance brokerage firm, Aon. That's one of our research sponsors. And we took our simulations of hurricanes in the future, some future climate scenarios, and gave them all the changes in hurricane frequency and intensity, and they put it through their exposure and vulnerability. So they have a database of all the buildings in the United States and so on, and which is proprietary. We don't have, but they calculate the loss. So this is on the y-axis here is the change in percent in loss from hurricane wind damage. And the x-axis is actually different statistics. So AAL is the average annual loss. This is the 100-year event, so the 1% probability each year event, and so on, and how much that changes. And there's two solutions, positive and negative, because of what I just showed you. That we have some models that produce more hurricanes and some models can produce fewer. So in fact, they pay us all this money and we can't even say the sign of the answer. It's kind of embarrassing. But there's still information here because the changes are not very big. They're around 10% or something, which is at least saying that maybe hurricanes are not the biggest aspect of the climate problem, if you believe this. But this is only wind damage. It's not accounting for flooding. And if you include flooding, it gets worse. There's some other interesting aspects of the results, but I don't want to dwell on it. I want to show you some of our work. So this is a vulnerability curve. Looks like this. This is a typical one. So this says what's the wind speed on the x-axis, and this is the fraction of the building destroyed. And all vulnerability curves have this kind of shape, where it starts at 0 if the wind is if there's no wind, then your building is fine. And at some very high wind speed, the whole building will be destroyed. And in between, it has to rise monotonically. So this is one particular functional form that was made up by Carrie Emanuel, a great hurricane expert. This is just a kind of a made-up curve, but it has to rise, and it has two free parameters, v half and v thresh. So one says, when does this curve start to rise? When do you start to get damage? And the other says, how fast does it rise? What's where do you reach the midpoint where you lose half the value? And in what I'm going to show you, we treated those as free parameters and tuned them. So we didn't know about all the buildings. This is a study on the Philippines. So we just tuned the parameters. So here this is our first study of loss. So we took the historical tracks hitting the Philippines. So these are all the hurricanes that have hit in the past. These tracks here, you can see the red tracks crossing the islands. This was a study with people in the World Bank and done by my former postdoc, Jane Baldwin. So for each storm, we make a map of the wind swath, where the winds are as you go across the island. And then we have two vulnerability curves, and I'll say why it's two in a minute. And then we have a map of exposure. What are the buildings? And we don't actually know all the buildings in the Philippines. What we use, this is a data set that takes gross domestic product and disaggregates it, downscales it using night light from space. So that's, if you don't have data on all the buildings, that's a proxy that you can get from public data. And so from this, we can calculate the loss for all historical storms. And what we did was, it's with the World Bank, and we calibrate the loss to try to calibrate our vulnerability curve to try to get the right losses compared to what actually happened. And this is one metric of loss, so it's a statistic called total damage ratio, TDR. But basically, red means we're calculating too much damage, and blue means not enough damage. So when we use one vulnerability curve for the whole, you want to make your model, take a step back. When you want to make your model as simple as possible, because you don't want to have too many free parameters, then you get overfitting and you don't really know anything. So we tried first one vulnerability curve. Assume all the buildings in the Philippines have the same vulnerability to wind. And if we do that, we always get too much damage up here. Manila, the capital city, is about there. So in that state, we always get too much damage. And this is a better result that agrees better. And what we did there was use two vulnerability curves, one for Manila and one for everywhere else. The World Bank and this is Jane who did the work, the World Bank, who we collaborated with, actually had household survey data, actual knowledge of something about the roofs on buildings, and there's good reason to believe that Manila, as the capital and the richest city, has less vulnerable buildings. So by using 2, we get better answers. So this is just the kind of games you play when you don't really have enough data, which is a typical situation in this field. I'm going to come back to this. Okay, one more thing I want to talk about, getting back to climate science. So doing this kind of work has led us back to do problems in climate science that we didn't think about before. In our work with the Aon, the insurance brokerage that I just mentioned, we modeled all this, we did projections of, as I showed you, of how much storms will change in the North Atlantic and the West Pacific. So this is a map we made for them of the change, the trend, the change over time from 2021 to 2050 in the model where hurricanes increase. And the map is, if it's red, it means there's more hurricanes. If it's blue, it means there's less. And you see it shows a big increase in the Pacific and a decrease in the Atlantic. And we showed this to our colleagues in the insurance industry, and they said, but this doesn't look like the past 40 years. Over the past 40 years, the Atlantic has been increasing, and the Pacific has been decreasing, which is the opposite of what you're showing us. So is the future going to be different from the past, or is your model wrong, or what's happening? And we thought about that for a while. It was a good question. And we realized that a thing the climate models do, so the climate models that are in the IPCC, if you know what this is, the Intergovernmental Panel on Climate Change, those models that are run all around the world, that's where we get our information about the climate, and we feed that to our hurricane model. And those climate models predict that the change in sea surface temperature, the temperature of the water at the surface of the ocean, which is very important for hurricanes, that changes in the Pacific in a pattern like this. So the red means it's getting warmer everywhere, but it's getting warmer more on the equator in the eastern Pacific. So this is the pattern of change over 30 years, but it looks like what's called an El Nino event, if you have heard of that. The El Nino is an event that happens sometimes where for 6 months or 1 year, you get a change that looks like this. And when that happens, you get more hurricanes in the Pacific and fewer in the Atlantic, crudely speaking. So it makes sense that if the models are predicting this trend, that we will get this kind of change. But that's not what has been happening over the last 40 years. Actually, the opposite has been happening. The pattern of actual change, so that was a projection of the future. This is the last 40 years of observations. And actually, it has been cooling in the east. So it looks like what's called a La Nina event, the opposite of an El Nino. And in a La Nina event, of course, you get the opposite response in the hurricanes. And so this is the observed pattern of change. So you get fewer hurricanes in the Pacific and more in the Atlantic. That's what our insurance colleagues would tell us. So we said maybe it's no surprise that we get the wrong answer for the, an answer in the future that doesn't look like the past, because the models are predicting the opposite of what has been happening. And we have now come to think, we realize that we have some colleagues at Columbia who have been working on this for about 25 years and had a whole bunch of reasons why they think the models are wrong. It's not obvious the models are wrong because the Pacific, because of El Nino and La Nina, it's always varying up and down. So to find the trend that's due to climate change is very tricky. It's like when you see the stock market go up and down, you don't always know what the long-term change is going to be. So it could be just the models are really right about climate change, but they're wrong by accident because the variability has been too much. But we now think the models really are wrong. We're going back to, I probably don't have time to talk about this in detail, but we're going back now to do studies of, to understand what the climate models are doing and try and see if we can force them to do the right thing that looks more like history. Because if you represent the uncertainty in the future projection by the spread, we have about 30, 40 models run around the world to represent climate change, and all of them don't look like the observations in the Pacific over the last 30 years. So if you represent the uncertainty by a spread in different models, but the observation, the truth is really here, you have a problem. You can't quantify the uncertainty. So we're trying to generate scenarios that look more like history, and I don't think I have time to talk about it, so I want to, well, yeah. We have a way of forcing the model. So this is what one of the American climate models predicts for the trend, being red here over the last 50 years, looking like an El Nino. But when we flux adjust it, it looks more like this, more blue over here. So we can get closer to, in other words, we're forcing the mean state, we're correcting a bias in the model, and that changes the trend. And the physics of that is interesting. So without going into the details of it, what we're doing is a climate science problem that was already somewhat known, but we hadn't focused on it, but we're focusing on it now because the risk problem made us realize that you spend all this energy and time and money to downscale a projection of climate, but the projection of climate itself has an uncertainty that the climate scientists don't understand. So there's an interplay between doing basic science and doing the applied science, and that's interesting. In the last few minutes, I want to say one more thing. So I was talking about vulnerability modeling and how we represented all the buildings in the Philippines with two simple curves. Obviously, that's very crude, right? There's millions of buildings, they're all different. So when we first started doing this work, this is a very complicated slide, and I don't want you to try to read it. I just want you to see that it's complicated. When we first started doing this kind of work, you know, we're not wind engineers. We're trying to learn about the vulnerability of buildings, so we talked to a wind engineer, this guy named Peter Vickery, who's one of the best ones, who's done a lot of work in the insurance industry, and he told us, this is how you model vulnerability. It's a very complicated thing, but basically you have to know what your building looks like, and you put it in you put it in a simulation of the flow, like if it was in a wind tunnel. You do a simulation where you model the pressure forces and the flow around the building, and you try to figure out when the roof will break off or when the windows will break, this kind of thing. And you do all this modeling, and you can figure out the vulnerability for one building. But then you have to know all the buildings in the country. I mean, it's completely impossible. You know, if you want to do the whole world, or even one whole country, that's not the United States or maybe some European countries that have all this data, you can't possibly do this. But you can imagine, this is what you do in insurance if you're insuring one building, or a few, or, you know, but when you want to do climate projections for a whole country, you know, it's too complicated. So, but this is like if you really would do it right, you can imagine it's a very, very high level of detail, right? You model vulnerability, think about all the storms, as I'm telling you. Instead, what do the economists do? So the economists who want to figure out the economic impact on the whole planet by climate change use, now they're somewhat more complicated, but the original models, which are still in use by a guy named Nordhaus, who won the Nobel Prize in economics for this, it's called an integrated assessment model. And here, I would argue this is still a climate risk model, but it's simpler by many, many, many orders of magnitude. So the loss here, he calls it damage, the loss is a function of the global mean surface temperature, that's this T. So just one number. Instead of all the storms and all the heat waves and all the floods and all the wildfires, it's just one number. The global mean surface temperature represents all of that. And the vulnerability, the exposure is just the whole economy, the whole global economy. And the vulnerability curve is a simple quadratic form here that represents the vulnerability of the whole economy to temperature. So just think of the difference in complexity there. The point I'm trying to make here is that in this field, people are kind of doing the same thing, trying to model the risk from climate, but doing it hugely differently, depending what field they're in. And maybe that makes sense because they're doing different applications, so they have different methods, but I think sometimes it's not always clear that the level of complexity is right for the problem, or just people did do it because that's the way somebody did it before, or they don't have enough data or something. So I want to close with these remarks. I gave you a lot of information, but what is the point here? What I was just saying, to summarize that, there's a lot of climate risk information out there. A lot of people are doing this kind of thing now. Modeling the risks from climate change, the possible economic losses, to figure out how to handle it. But it's done hugely differently in different sectors. So the economists do one thing, the insurance people do another, people in agriculture or infrastructure, you know, or health do it differently, even though they're all doing hazard, exposure, and vulnerability. But it's not just different sectors, they use very, very different levels of complexity and sophistication. A lot of this work is done in the private sector because somebody has a contract you know, to do it, and so it's proprietary, which means that we don't have a great culture of comparing results. As we do in my field, in weather and climate, we're great at comparing results. Everything is public, everybody shares data, we have the IPCC, but in this field we don't. So it's a problem because if you can't compare, then you don't really know what's good or bad, or what's the advantage of doing it one way or the other way. So there's not enough systematic comparison. The other thing that I spent some time talking about is that some of the most important uncertainties are in the basic climate science. So a lot of the work that people do in this field is they just take the climate models and they downscale them. They say the climate models don't represent the extreme events and the losses, so we'll put all our energy into that. But if the climate projection underneath has systematic problems that we know about, and something like the change in the Pacific between El Nino and La Nina has impacts all over the world. It will affect, you know, even the wildfires in California and Australia and Indonesia. It will affect fisheries. It will affect storms all over the world. So if we don't know the trend in that, then all the downscaling is not going to help us. But it's very hard to quantify those uncertainties because we don't have any models that look right. So in other words, we want to do everything quantitatively, but there's fundamental understanding. So this sends us back sometimes. What I have found is that I started as a basic climate researcher and then started doing this kind of applied work, and then came to the conclusion when talking to decision makers, people in the insurance industry that have to actually manage the risk, that sometimes the things you really need to tell them about are the things you don't know instead of the things you know. So it's an interesting field where we have very basic and very applied problems that have to sit right next to each other. So in my group, we're working towards synthesis and thinking about how can we make a coherent field where we do a little more of this in academia. That's why I put that in the title, instead of only doing it in the private sector. It's not only, but it's a lot of it in the private sector. If we do more in academia, we can compare our results a little more and try to understand what's the advantage or disadvantage of doing it different ways, depending the problem you have. And so I think this is a kind of an opportunity to make, in a sense, a field. I mean, it's not that the field doesn't exist, but it's not coherent. So I put my conclusions there again, and I have some credits. And I just want to say thanks for having me, and I hope we can have some good discussions, you know, over the next day and a half. Thank you.
Thank you for a very interesting talk. Yeah. Any questions to the speaker? Okay. I would like to ask you, can machine learning help in here, or these events are so rare that you cannot really rely on machine learning to come up with models?
Machine learning can be used in lots of ways and is being used in lots of ways. So our hurricane model, for example, I didn't explain how it works. It's not really machine learning. It's more traditional statistics that are in there to derive the relationships that connect the environment to the hurricane. We have all the past hurricanes. We have what was the climate they were in when they happened, and we find those relationships. So you can use machine learning for that. The amount of data is not that much compared to what you want for a machine. There's not that many hurricanes, but there's a couple thousand maybe in the historical record. So you can do it there. You can do it for many other aspects. Now, of course, I think the exciting thing to do now is that the way we do it and the way the whole insurance industry does it is about to be obsolete, because now there are weather models that are all machine learning. So weather forecasting up until now is done with physics models.
But not for rare events, I guess, right?
No, but this is the thing. It can be done because now you have models that are getting to high resolution that can forecast the weather very well. And they're not so good at climate change, but you can put the climate change in various ways. And then, because they're so cheap to run, you can now simulate a huge number of hurricanes directly. And then you don't have to make these empirical, you can just pull the hurricanes right out of there. So I think this is a field where machine learning can be used lots of ways. But we have to be a little bit clever about it and understand what it can do and it cannot do. And this is where I think doing it openly and comparing results is very helpful, because there's as always with machine learning, there's ways to abuse it and get wrong answers if you are not careful.
It feels like there's a question about the scale at which going from large scale parameter change, producing a model and going down to a specific location, or only looking at specific factors.
Yeah.
I feel like that's a common problem in going from large scale to individual, especially with buildings, right? Because there's large scale effects to the individual. Do you feel like there could be disclaimers, or like, at what scale do you use these models, or in what context and level of detail? Like, is there a roadmap potential for like how to use these models?
So you got the point I was trying to make. There isn't one, And I think it goes both ways. In other words, it's not just that sometimes you don't have the data or the computing power to do the whole problem at the finest scale where you really believe things, but sometimes you don't have the data or the knowledge even to constrain the problem at that scale, and you might be better off using a more aggregated, in other words, it can go either way. It's really not obvious. It depends what question you're asking, and I think what would be good is to have a systematic understanding. In weather, I come from this, we sort of understand the trade-offs between resolution and computing and observational constraints. We sort of know how those things interact, and in this space I think we don't. And so that's what I'm trying to get at, is that maybe with a little more communication between the different sectors, a little more systematic. Because right now what happens is, people who do this, somebody gets a contract, they have to get an answer by some time, and they do it. Maybe they do something that's smart, but a lot of times they don't publish it, or you don't know what they, and so the next person who does it might do it the same way, but it's not really, or might not, but I think those trade-offs are not clear. Yeah, I mean, maybe they're clear to the people doing the particular thing, but there isn't a whole field of it. Thanks for the question. That's my point.
One quick question. In your data, have you noticed some real non-stationarity that says that proves that there is a climate change, etc.? I mean, is there because there is a lot of variability which is seasonal, but have you seen that this is moving in some direction, a specific one? Yeah,
that's an interesting question. So there's no question that there is climate change, but this is not the way I would prove it. So, the clearest way to see the climate change is simply to measure the temperature and average it over the planet and measure that. Then it's very clear. But the extreme statistics of extreme events are like the most delicate thing. They're the most subject to variability. And for example, in the United States, losses due to disasters have been going up very, very fast. But that's not the best way to prove climate change, because a lot of that change is due to building more things in risky places. And so there's probably a climate change signal on top of that, but you have to pull it out. I mean, it depends what you're looking at. If you look at wildfires in the west of the US, those have increased so fast that it almost certainly has to be some climate change. But with hurricanes, you can't really, it's hard to prove. But if you look at the temperature and the ice melting and this, then it's very easy to see. So I think this kind of work is not the right way to prove climate change or not, but it's the right way to understand how to deal with the impacts. To do adaptation, you have to, because nobody's adapting to the average global mean temperature. They're adapting to something more specific, and often it's extreme events.
Thank you very much. Our rector is here. Would you like to say something, or just continue with the presentations? Say a few words.
I'm familiar saying a couple of words. Nowadays, when we live here, when we start the session, it's wonderful. And I'm saying wonderful because I see this a great opportunity to getting closer between NTUA and Columbia University. Columbia University is top university worldwide, and we have a lot of things in common, and we can excel research and academic activities for the benefits of both communities, especially for us, since we are trying to increase extroversion and many other things which lead to the development of our institution. Thanks, warm congratulations goes to my colleagues and vice rectors, Professor Barbarigos and Professor Lagaros, who initiated and organized this great event, and I hope more students will come in the future. And let's commit ourselves that we will continue and organize it every year. Hopefully next time in New York. I also thank my good friend George Deodatis, who was so kind to welcome him warmly recently in New York and Columbia University, and the fruitful discussion we had together. And of course I see here Professor Timisis, καλώς ήρθατε, and all the other colleagues here. Thank you so much.
Let me call to the podium the next speaker from NTUA.
I tried to sneak in, but okay. Okay, let's kill this. There we go. Let me just say also that I'm very, very happy to have met at last Professor Varvarigos, because for those who don't know this, he signs the contracts. Super. So at last we know who gives us the money. Now, super. Just to connect a little bit with what my predecessor was talking about, Professor Sobo, essentially what I'll be showing you is a little bit the same idea, or the same set of ideas, let's say. But let's say the same problem, you can look at it from a telescope, meaning regional, country level assessment. You can also go at it with a microscope. It's all an issue of radius and focus. And when you want to go, for example, and look at the Philippines, you can maybe hack it with 2, 3, 4, 5 vulnerability functions. If you want to go and look at a specific portfolio of buildings, which, as he rightfully said earlier, it's quite often done in the private industry, and it's also very, very relevant when you're discussing critical infrastructure. You want to be able to go deep in, and you'll be able to say that each asset at risk, that might be building or infrastructure, you want to be able to say something smart. You want to be able to have the capability to know what's happening for specific forcing functions coming from the environment, and be able to also say something about the portfolio, the collection of assets, and I'll explain where that goes. Now, and again, the same idea, you got weather hazards, you got geohazards, you got your climate change, you got the tools and services to take care of these, and you want to improve on that, and you want to go through better preparedness. You want to help the operator of the system to be better prepared, meaning to have some idea of what is coming at you, at him, prepare restorative actions, meaning help them to be able to fix it when it happens, because you cannot always avoid it. And of course, in the end, discuss an issue of comprehensive risk management, not just figuring out the risk, but also managing it at the other end. Now, to give you an idea, like a very simple conceptual idea of how this works, you got your hazard, meaning if I want to do climate hazard and weather hazard, I would go to Professor Sobel, I would go to somebody who knows how to do this in general for my area and my side, and I'll tell him, give me scenarios. And he'll give me that. Then I need to figure out the data, the so-called exposure or assets at risk, and see what is there and is exposed. I need to integrate all that in groups. Why groups? Well, it would be lovely if I could do each and every one separately. You can't. You got to group them up into similar things. For example, similar buildings, similar roof, construction types, construction codes, heights, etc. Put them together so you manage the problem a bit more efficiently. There are the rare cases where you can do each asset separately. Typically, that's called nuclear power plant, refinery, or a very important, I don't know, port facility. Okay? Then you got to network your assets together, meaning typically utility or infrastructure network, that would be transportation, water, electricity, power. And then you want to interconnect them, because typically, as people will tell you, when communication goes down, things don't work as well. When power goes down, practically nothing works. Okay, water works, but that's about it. Yep. So, you put all together, you get your city model, your city level model, and then you add up the extras. And the extras are, pretty simply, if you damage something, it's not just the damage that you need to repair, it's the loss of business you need to take care of. and the loss to overall community. And then you get your so-called, well, now it's a fancy word. We used to call it city digital model, now it's a city digital twin. There you go. Same thing for industrial infrastructure. You got your hazard, you got your asset at risk, various types, and now you got to connect them. And over there you need somebody who understands, a process engineer, a chemical engineer, somebody who understands how this works together. He gives you the blueprints, he tells you how to connect them. You do it all together, you get, for example, in this case, a refinery or a chemical processing unit integrated model. Meaning, you lose or damage or you put out of operation any of those assets, you're immediately able to tell, after a bit of running your model, how much loss in productivity you've got and for how long. And it can get even fancier if you want to discuss specific infrastructure like a transportation system, quite typical, or an inland waterway. Again, you set up your assets, you connect them, and then you have a difference in scale, because quite often these are spread out over hundreds of kilometers. You put them together, you interconnect them, and again, you get your transport integrated system. And in some cases, like the Danube, for example, a beautiful inland waterway system, that is of the order of thousands of kilometers. It's pretty long, pretty large. So things that happen in Germany, a few days later, can influence something that's happening in Romania, where the Danube goes out into the Black Sea. Now, under the hood, and I'll show you how this is done and how we do it if you want to talk specifically critical infrastructure, it's a slightly different process, meaning you don't take the process of integrating things all together and trying to group them up very nicely. You try to disaggregate. You try to go to the detailed microscopic level as much as your computer power and processing capability, okay, also how much they're paying you, allows. Essentially, you got your assets, let's say 1 to n, you got your hazard records, meaning events, potential events that can happen, put them all together in a geotechnical structure simulator, and you get your asset response. In this case, just to be clear, it's all scenarios are in play, everything. Smallest event is just a breezy day to the worst possible one. It's a huge hurricane. You got, if you want to do multi-hazard, that's the typical case, you got your earthquakes, landslides, sea level rise, etc. All of those responses get included, plus what we call a stochastic event set, meaning you want to disaggregate also your events. You want to talk storm by storm, earthquake by earthquake, wildfire by wildfire. Why? Well, because if you do the insurance style, insurance only care about essentially aggregate losses. The good thing about aggregate losses, if you aggregate wide enough, and if you aggregate over many, many assets, things get smoothed over. So the individual differences that will make your life difficult kind of disappear. If you're talking about a critical system, a critical infrastructure, any little piece that gets broken down can generate a domino effect that can kill your entire system. For example, you lose your power transmission from the power plant to your city, there goes the city, no power. This doesn't happen when you aggregate losses. That one is, this goes, the rest goes. So, in those cases, you need to do what we call event-by-event risk. And, oopsie, you put them all together in the risk engine, you steer the pot very nicely, and then you get impact. And you can get impact from nothing to a lot and to crazy, and you have all those information together. Now, the fun part is that you build this crazy database of gigabytes, or worse, and you introduce the fun part. Sensors. Why? Because everybody wants early warning. Right now, as we speak, I know there are companies out there who have servers in Amazon or pick a cloud server that you want. They're running dedicated models of near real-time risk, short-term risk assessment for hurricanes, flooding, whatever. And they update those models and their projections as things move forward, day by day, especially funny in the hurricane season. In this case, you want to introduce sensor input. It could be as simple as a weather forecast, or it could be early warning for an imminent earthquake that gives you a few seconds, because you got sensors over there and your infrastructure is over here, and you get a few precious seconds to say something smart about what kind of valves you want to turn off and what kind of trains you want to stop, as they do in Japan. In such cases, you go back to your database which you have grown into a nice big tree of possibilities, and you start chipping away and pruning down. Meaning, typically you get, by the way, 3 categories of sensors. That'll be your response sensors, meaning you have something on your asset and you measure its response, meaning you start removing potential scenarios, what can happen to your building. By the way, green is good, black is really bad. Once you get your sensors in there, that means you can tell something smart, especially for somebody like Professor Smith over there, who can tell a little bit better about health monitoring and how you can interpret actual sensor data into infrastructure damage states. Now, you also get your hazard sensors. These are more typical. This could be a weather station or a seismograph, which essentially prunes down your stochastic event set. It can tell you that, no, it wasn't a big earthquake, it was a small one. It wasn't a huge storm, it's a small one, or it's a big one. We have the data. And of course, you get impact sensors, the simpler of which is you got somebody on site who can tell you what's happening, or even a camera that's actually looking at things, and regardless of whatever the rest are saying, which is just inference, you're trying to figure out something, a camera will say, I know that your sensor said a magnitude 7 happened and everything should be destroyed, but it's there, I can see it. Meaning, it can prune down what actually happened, assuming it's a good enough system. By the way, some of the best sensors, you've been seeing them around, unfortunately because of operations happening, you get a satellite that's looking down, and you don't need to tell that somebody threw a bomb there. You can actually see things as they get destroyed. It's all over the news. That's the kind of impact sensors that you want to introduce in this kind of information in the system. Of course, I won't say more about climate change. You've already heard enough about it, but we're more or less working with IPCC scenarios. You want to work with them, hopefully have them unbiased and producing good information for you. You want to downscale. Again, statistical dynamic downscaling works quite nicely, meaning you introduce also computational fluid dynamics information together with your stochastic event sets provided by Eurocortex, and you can take down and figure out, hopefully, reliable statistics of what the weather is going to be in the coming years. And of course, you got your flood hazards. Annie Leopold over there, she knows better than I do, but we trust her to produce good flooding for us. And of course, event-based hazard, at least that one we can do with a bit of help from seismologists. Thank God for them. They give us nicely correlated event fields where you can tell that things are happening at the same time for a multitude of potential earthquakes. And by the way, the uncertainty is sometimes ridiculously large, but you get that as part of the game. Put it all together, and what you're seeing are alternative timelines, parallel universes, if you will. I don't know if you're into science fiction, but potential timelines of how your infrastructure is going to look going forward. 10, 100, 50. Actually, it's much easier if you think about it. Alternative next decades or alternative next years. Or if you want to do climate change where the risk is, the hazard is non-stationary, meaning it's changing because of the climate change, you want to see alternative 2050s or alternative 2070s, years into the future. Finally, you get to do your aggregation. After you've done your pruning, you've removed the relevant stuff based on your sensors, you can aggregate the results of different events that are compatible with what your sensors told you has happened. And now you get statistics. And hopefully you get them good and reliable enough. Meaning from your disaster hitting your urban system, you actually have good statistics, good values of, including, as a by the way, it often seems that a very tight result, let's say -1 to +1, I don't know, or 10 to 10.1 seems like a very good result. Not in our business. Typically that means you don't have enough uncertainty in your system, you're missing something. A very wide result is also not good enough. It means you don't know what's happening. You want something in between, and it's experience. Lots of good models to do that. So, assuming you got all that properly, and you set everything right, you get your direct losses, and typically the part you're missing is the so-called indirect. Indirect is the loss of business. What's happening inside your society or community because you got stuff that is preventing you from doing business. Well, here's an example. This is Rhodes, Greece. By the way, Rhodes is, well, where the little nice arrow is. Really nice touristic island. It looks good. If you've never been there, highly recommend you do go. And here is the economic data from the government. And you can tell very quickly that it's retail, accommodation, food and beverage. And those are massive, meaning tourism is king. We're talking about an island that essentially quadruples its population or more every single summer. And here's what happens after every single asset gets damaged in your average little disaster, hurricane, earthquake or so. You get a drop in its functionality, and then you start recovering and fixing it, and at some point it gets hopefully back to where it was, sometimes not exactly so. You can track that. Well, remember simplicity of modeling, you gotta make it simple, through infrastructure indices, input and output, meaning economic input and output. I'm not gonna trouble you with the details. I'm just gonna say that looking at the entirety of a sector, let's talk about the hotels. Let's say you got 10 hotels, and on day 0, because of minor damages and big damage and whatever, just windows cracking, only 10% of your hotels can be used. That's it. 10% of your sector is actually, of your accommodation sector, is functional today. That's gonna change tomorrow. They're gonna fix the windows, remove the little mini things that prevent you from working. They're gonna go up to 50%. Most of it recovers very fast. But that 50%, until it gets 70%, is a little bit stubborn. Until it gets to 100, lack of funds, deeper damages, lots of things, it's gonna go slower and slower and slower. Put that all together, it means that there is a sector interconnectivity. If your bakery is damaged, if your grocery doesn't work, they're not gonna feed you your bar. Your bar has a few stocks of, whiskey going on. Then your, Scottish tourists will decide that I don't care anymore. I want to go back. They go back home, your bar goes down, and your activity at the bakery and grocery go down. And okay, I'm oversimplifying here, but there is a back propagation effect where you lose business and things start shutting down. And this has been observed in actual communities, that there is a certain level of damage that beyond which you go, you start getting massive feedback, negative feedback back into the process. And you'll see what happened in Turkey and the kind of ghost towns they have now there because of what's going on, what went there during the earthquake. And put all of that together, you get a dynamic socioeconomic impact model where essentially each sector can influence adjacent ones, and based on published economic tables, you can see the trouble traveling down and also the recovery traveling up. So initially you get all the trouble going down, and then you see back everything coming up, and hopefully coming up to 100% actual return to natural state. Of course, while we do all this, risk and insurance, and it's all done in layers. You want to categorize your risks based on return period of how often it's going to happen and the magnitude of this, and you want to implement different risk handling, risk management mechanisms. To give you an idea, on the left, you get the high frequency, low impact risks. Think of it as a dent in your car. Then you get a little bit more than a fender bender, you damage your car actually, and over there you get the complete losses. What happens is the so-called risk retention is the part that the insurance company will not pay, meaning you know that if you scratch your door, nobody pays you. They're so-called deductible. Officially, it's called risk retention. Then you get the part that the insurance will pay. That's the risk transfer, meaning your risk is transferred to the insurance, and they transfer it, by the way, to the reinsurance. Then, to higher ups, you go to essentially you cannot anymore rely on the insurance broker, the insurance, because they will go bankrupt. They don't cover that. Those higher, let's say, percentages, those big events, essentially they require international or governmental, at least, financial assistance. And if you go to true catastrophes, these are beyond any limits of coverage. You need international help, you need something different, and there's a very good chance you won't really recover. Yes? The interplay of, let's say, government and insurance, it's exactly that, sorry, oh shoot, I managed to destroy this. but it's exactly the part that says risk transfer. There we go. So, just to give you an idea, it's not just classic indemnity insurance, the classic one we use for our houses or our cars, if you will. There's also issues of why not we try new products. And you talk to insurers, they often discuss parametric insurance. The trick is that you define a trigger, meaning seismograph so-and-so measures at least this much, or wind vane so-and-so measures at least this many kilometers per hour. And then people pay you based on what the instrument recorded, and not wait for 6 months or 1 year for somebody to come in, survey the damage, and give you a pricing. By the way, I don't know if you know about this, but Daniel storm and the flooding that happened in Thessaly, not everybody has been compensated. I have family up there. This is extremely low and slow. So there are ways to design products that make sense for the insurer and the insuree, anyway, who's getting insured, to be able to do quick resolution. But you may be increasing your basis risk, because if you don't do it right, it's not good. Again, we're not trying to beat the system here. The plan is to make both insurer and the guy who gets insured, we try to get them both happy and make sure they can manage their business and survive. So we want to do this right, meaning without bias. In essence, if you do this work right, you can model losses in a proper way and help people design proper financial products. And just to give you an idea, the whole point is, what's the attachment point, meaning where do you start paying losses as an insurer? What's the exhaustion point, where you stop paying losses? So think 20% and 80% roughly. And of course, what's the coverage limit? That's where you say, that's it, that's how much I pay, bye-bye. Those are important numbers, and you need help to figure them out. Now, just quickly, I just show you one aspect of how you do risk management. You want to do this properly, comprehensively. This is just one part, is the financial tools to help foster quick recovery. There's all sorts of aspects to this. I'm not going to try to cover them. You want to minimize long-term costs. You want to have synergy with other risk management mechanisms, and I'm just showing an example here, because you want to manage recovery, preparedness, measures of response, and all of those are important, whether you're talking a country, a city, or an infrastructure system operator. Okay, oh, and by the way, just to say, I'm not alone in this. I have some really nice industry help, so just to say thank you, Red Risk, for lots of those nice slides. This is not just theory. In the end, people are asking you to do this kind of assessments, so we've done a lot of work for Norway, city of Tonsberg, actually city of Venice, Highway Madrid to Barcelona, the city of Granada, Egnatia of those, the motor oil refinery, even a couple of temples and nice monuments for archaeological efforts of antiquities, and of course the city of Rhodes, beautiful place. And of course, nothing works without partners, so thank you, Mr. Vice Rector, for signing those contracts for us, and of course, our funders who love us very much, hopefully. Thank you.
Any questions? Please.
Sorry? Politics. How's politics?
And even all the different locations that you've worked in, and how do you do your recovery model given these?
Is this being recorded? Okay, so I have to be generic. Let's say that there have been certain Pacific islands where we've done this kind of business with good friends from the industry. And typically, politics comes into, let's say, redistribute things in a way you wouldn't think possible based on pure mathematics. So let's say, for example, your analysis says, do that, reinforce this, and fix that. And typically, they will come in and they will tell you, yeah, well, you know, that place you've left alone, and you haven't done something. You go like, yeah, of course, because it's a very little vulnerability. Yeah, but they're gonna feel like everybody else is getting something. You should do something for that. So you have those things, and it's really the things that you don't think about at all because you just focused on the mathematics. So I won't say that it's bad. but it's really a way of, let's say, let's put it this way, it's bridging the math and the engineering with what's happening really in society, so everybody is happy with each other, let's say. Yeah. It's a big issue. There's been a case where we had like version 30 something of the how to distribute the funds approach, and it was changing every time because of politics. Yeah.
Very interesting presentation and a lot of common areas with what we're doing at Columbia. Indirect costs and losses that you mentioned. So the approach is you estimate the economic activity, you have a disruptive effect that happens. The question is, what percentage, let's say, of the daily economic activity is lost? And I assume in the beginning it's going to be a large percentage, if it's a big disruptive event, and as time goes on and repairs are done, this is gradually recovered. But do you have any guidelines on what percentage you are considering lost in the beginning and how it recovers?
So far, let's say, every time we look at this program, we come up with new variables to introduce. For example, overproduction. Somebody loses business, the guy next door pops up to take care of that, so that happens. Stock, what's the stock they have? Access to other routes of transportation, and for example, you're talking roads, you get a small disaster, many things, nothing changes, they can fix it. You get a big one, a company will come in from Athens and will bring in capacity to construct and fix things because it makes sense for them. So every time we look at this problem, we start seeing new things and new avenues and also cultural issues. I've had discussions with friends from developing countries and not developing countries the same as any other one. And the way they respond to disaster, how fast they work, how fast they recover, how they handle it, it's all over the road. So in the end, the best answer I have is you gotta calibrate. You gotta calibrate, and if you have something recent that you can use, so much the better. If you don't, yeah, you have to put a little bit of a white part of uncertainty around that.
In New York City, we had the example of Hurricane Sandy in 2012, and in downtown Manhattan, where the subway, the metro system, has been flooded, and it was not operational for at least a week. There was a very, very significant loss of economic activity. But the part that it was not easy to calculate is that a lot of the economic activity produced in this part of the city was done with remote work. Because Wall Street is in this area. Wall Street doesn't mean that a lot of economic transactions, I mean, the stock market closed, but a lot of economic activity is going on online. So I agree with you, it becomes very, very difficult to determine what percentage is lost. The actual stores and businesses closing down, yeah, this you can calculate, but there is a lot of else that might not be as obvious.
Actually, I've heard this also, we've done some work with that, with the industry, and unless you're talking about a really 24/7 kind of industry, that'd be refineries, by the way. They are practically 24/7, they run all the time as much as they can, and they overproduce as much as they can. Unless you're talking about, those kind of production facilities, typically disruptions of the order of a few days or even a week, the equivalent of a long holiday, they tend not to matter much. But you're talking the critical industries, that pile up quickly, so there's a difference. Every system is its own.
I also wanted to ask you something.
Anything.
Both you and the previous talk justify this research by saying that it's important for the insurance industry, etc. But if somebody is not interested in the insurance, let's say, industry, and if you come from the side of the public and you have some investment that you are willing to make, and you want to make it so as to minimize the cost, the total cost. Do these models, I mean, apply also there? Or
oh yeah,
it's the same
actually, some they're investors typically. The first thing they do anytime they want to buy anything, and they will try to get a risk assessment of that. Not that expensive, not that kind of a integrated big thing, but they want to figure that out.
If the state is the investor that wants to make some public works, to see what is the best value for
to give you some idea, for example, a level of government. Have you heard of NEOM, the area of Saudi Arabia that has been generated as a future city, etc.? They did a wide risk assessment for obvious reasons: drought, earthquake. It's the only part of Saudi Arabia that has earthquakes. And all kinds of climate change issues to figure out whether it's viable and makes sense to put in those billions for sure, maybe $1 trillion that you need to fix that. So that works. There have been cases of Indian states where they have said that they have so many chemical industries all around the state that they want to have a best emergency plan for any kind of disaster that hits them, and they want to have it updated near real time. And those things do happen, and they do get it. And even now, with Professor Gulams and Professor Bouris from the Mechanical Engineering Department, we're running a project where the European Union is testing the idea that you don't want just the government to pay for your infrastructure upgrades or your climate change adaptation measures. Maybe you want to get in some private funding because they benefit a lot. So let's say Google or I don't know, whoever benefits from that, try to bring in the money. So it's getting interesting.
Out of curiosity also, you have different networks. You talked about failure cascade, etc., how one affects the other. But you have one network, you have another network, I don't know, transportation network, electricity, some other utility. Do you think, what are the interesting combinations, let's say, or networks of networks to consider, in your opinion?
It's getting crazy now. Let's say, for example, transportation. I typically go to Professor Vlachogianni over there, and all the craze over there in that region is multimodal hubs. They're discussing inland waterways, marine traffic, railway, all together. The plan is you want to have an actually connected Europe when you want to bring in freight at the hub and then be able to have alternatives, because that's the only way to get it resilient enough. Anything trouble, I don't know, call it a strike, call it a disaster, happens, you want to be able to transform and shift and, let's say, remove the so-called silos in transportation, where you put something in this one, in a truck, it stays in a truck, doesn't change to a railway, even if it's cheaper.
About different networks?
If you're talking different networks, typically the most critical one is power. And funny enough, it's becoming communication, because this happened in the earthquake in Chile. They figured out that because they couldn't communicate with the workers to tell them where to go to fix things, they ended up having a week or two more of waiting time to repairs for absolutely no reason, just being able to talk to people. So yeah, it's getting pretty complicated. Thank you. Thank you very much.
There is another question.
It's not a question, it's more like a comment from the point of view from our discipline, chemical engineering and material science. And we have the feeling that by increasing the scale and fortunately lowering the resolution of things, of understanding things, you may tend to underestimate things. For example, what I'm saying is sometimes we shouldn't forget that we're not doing maintenance of infrastructures. We're not doing damage repair afterwards. So when you come and you have the hazard, and usually you assume a hazard like a hurricane or a flood or an earthquake. But in order to see what you showed a very nice curve about going back to the original state. What if you didn't see the cracks? What if you didn't see the damage of the building there? And then you continue on with your own life, you work with the business and so on, and then the next earthquake comes or the next hazard comes of a lower intensity and the building goes down.
Oh, it's very easy.
I understand the difficulty, because the more you look at the bigger picture, networks, cities and so on, the more difficult it is to look down to a certain building. But we shouldn't forget that buildings are living things. They are, they're very sensitive to the environment, and we should pay more attention to that.
The solution is sitting right behind you.
Yeah, no.
Is this guy. So I go to that guy, Professor Gulamis, I have him on speed dial, and I say, bring up your drones, sensors, whatever, satellites, do your explainable AI, and tell me whatever is in this building. I don't know.
We need more information whether the thing is done. We don't know what is done, but we assume things and we
Remote sensing. I go to Professor Gulamis.
Multi-spectrum, not only temperature, but
this is remote sensing. Even now, we need in situ sensing.
Embedded sensors that understand stress, understand temperature, humidity, damage, materials, and so on. Remember, materials age by themselves. They don't wait for a hazard plan or whatever. Things may happen without any hazard.
May I comment? Does it comment? Our things, okay? We have sensing to make our control. So why our buildings, our infrastructures has no such sensing information? You know, because we not only remotely to monitor and to survey something, but our things, you know, to have in situ sensors to.
We will have a talk tomorrow, right? A presentation tomorrow about the
Okay.
And I will also have comments, not tomorrow. Because we don't need only sensing, we need everything. And we need in an entire ecosystem. This is the complexity that we are.
Yeah. Professor Andrew Smith from Columbia tomorrow will talk extensively along these lines.
So,
for break.
Before the break, yes, can I please ask all the speakers? Yes.
Keep the time, we come back at 4:30. But
Can I please ask all the NTUA speakers and all the Columbia speakers to come here so we can take a picture with our photographer, please?
dissemination opportunity, yes.
Please, and the vice rector, all of the Columbia, please. All of the speakers, all please.
All right, great. Thank you so much, and thanks everyone for coming out to this meeting. I'm very excited to be here, and yeah, I think there's a lot of overlapping interest. So I'm going to speak about something very different, and we'll hear more about this also from Professor Howard later. But I'm going to speak about something much more practical and much smaller. Last talk, I was very impressed. We heard about the bankruptcy of entire insurance companies and countries, and here we're going to talk about very tiny things. But I want to speak a little bit about some of our work in Internet of Things and urban climate mitigation specifically. So I had a project in my group, and one of the challenges that I gave to my students, this was a project that I gave to a master's student, and I asked him if he could make a sensor for $1, but with a computer readout, like a digital sensor for $1. And so anyway, so we worked on this for a little while, and we wound up making this system here. I didn't put a reference on it. Oh, can we switch to the slides? Sorry about that. So this sensor here, and the idea behind the sensor is pretty simple. Basically, one of the amazing things about electronics today is they're extremely energy efficient and they're extremely inexpensive. So the microcontroller that we use here, the AT Tiny, it has a quarter of the power of a Cray 1, but only costs 40 cents. And so what this device has is one amplifier. It has a couple of resistors, which are almost free. There's the circuit board and this microcontroller. And it has here on the bottom, you'll notice 2 areas where there are resistive patches. And so what it does is it creates, using the USB plug, it takes the 5 volts from the USB, and you'll notice that one of the rails goes to the bottom, one of the rails goes to the top, and then it measures the voltage in the middle, and it tells you basically what the ratio is between the resistance of whatever you put on the top resistor and whatever you put on the bottom resistor. So the whole thing assembled is less than $1, and the board itself, when you plug it into the computer, sits in the USB port. And it pretends to be a keyboard, and so it just spits out numbers. And so then the other half of this is to figure out how to sensitize it. And so what we worked on is we then went, and we have in our paper we have 5 different sensors. So you do, humidity is the easiest, because what you can do is you can put down, you can print material like PDOT in that case we use, which is an organic semiconductor, which is doped essentially by water, and then you can put a piece of tape over one of the 2, but at least when you first print it, when you first print it, they have the same resistance, so the voltage is at 2.5 volts, since the USB rail is at 5, and then since only one of the 2 sees the exposure of the water, you get the resistance up and down, and we show that you can use this for glucose testing, for humidity testing, for water quality, for a number of other things. And anyway, so it was kind of cute. It was, we put it in for we won some awards for it, which was great. And in the end, we found one real application. It was actually the core of a project called NOSI, which was Horizon 2020 project out of AIT, and they used it essentially together with some of their materials to detect the smell of trash in trash cans. So the NOSI program basically looked at how to optimize the route of the trash trucks. I know, it's a very glamorous project. And part of optimizing the route is figuring out how to reduce complaints about smell. And with AIT, which has a whole institute on artificial smell, they were able to make some receptors, and we weren't really sure what else to do with it. So fast forward a little bit, we got really excited about this idea of doing ratiometric sensing. And so where the initial $1 sensor used a resistive ratio, we also got interested in using a capacitive ratiometric sensor. And with a capacitive ratiometric sensor, there's a lot more that you can do, because many of the materials that are resistive actually also have an imaginary impedance change when they are exposed to an analyte. But actually the most straightforward one is to use it as a hydration sensor, a water sensor. And so we also, my students also got really excited about winning contests. So there was a contest that Verizon, which is like the local, not local, but it used to be the local phone utility, but then it bought like 4 others. It's now like a national brand again. So anyway, so they had a contest. Can you make something with IoT that's useful in the house? And one of my students made something we call the plant spike. And the slogan of the plant spike is your plants can't speak, but plant spike can. And what she really wanted to do is to use capacitive sensing ultimately to measure how much water is in the soil. And so, you know, the basic idea was, we initially thought we could make it for maybe $2, and $2 is a little, because it had a radio, it's a little too cheap. But in the end, we made a very simple sensor, and the idea was to have it sort of make the complaints that your plant had, not just have your plant die inexplicably. And so this is the first version, so it's about $6. And most of the cost wound up being the radio. So it has we use a microcontroller that has a built-in radio, which has some cost. But the real key part here is the humidity sensor is built in. And the humidity sensor is part of the circuit board, and it has no galvanic connection to the soil. And the microcontroller, we basically repurposed what was intended to be a touch sensor in order to measure the humidity, and because it has no direct connection, it doesn't corrode, and it doesn't get damaged in water. Now, we also did one other thing, which I think is pretty interesting, which is we also reprogrammed the algorithm for communication. So does anyone have like an Apple AirTag or that type of system? Anyone familiar with USB beacons? So USB beacons normally send out a signal and they give their identity. And what we did is we were able to get a UUID, and then we basically spoof the UUID to also include the data about the plant. And so there's no two-way communication. This wakes up, it sends out this, I'll call it fake ID descriptor, and then it goes right back to sleep. And so we were able to actually eliminate 3 of the transactions that normally happen for a USB beacon, and that allows us to really stretch out the lifetime while still getting data out. So, you know, it's kind of a nice system, and we won the contest, which is great. But then the question is, okay, like, the student really wanted to graduate, and just thinking, you know, how do we make this into something more glamorous? We were very fortunate to work with Trish Culligan, who was at Columbia at the time, and Trish was looking at a serious but somewhat obscure problem in the city, which is that, you know, New York City had a program at the time to plant 1 million trees. Now, a lot of the trees go into parks, they go into open areas, but New York City is mostly paved, and it's covered over almost everywhere, the street, the sidewalk. And so in order to put a tree in the middle of the street, you have to dig what's called a tree pit, which is where you open up the cement, or in some cases you don't pour the cement, but in a lot of the city that has to be removed. You put soil in, and then you plant a tree. And these tree pits are very varied. Some of them, the soil goes down extremely far. Some of them, the soil is extremely shallow, because in a lot of the city, you actually hit bedrock relatively quickly. And in other parts of the city, the under layer of the infrastructure was already built, and you can't get to the soil, even if there's soil underneath, but there are utility tunnels, and there's lots of other infrastructure. And so how well the trees grow varies very dramatically across the city. Now, so Trish was looking at 2 things. The first is basically, you know, what determines whether the tree lives or dies? It's extremely expensive to plant a tree, $6,000, $8,000 on average. By the time you get the crew, they're in New York, they're all unionized, which means they're all paid real money. There have to be like 6 of them at a time. Someone holds the track. You know, it's a very expensive operation. And a lot of the trees last less than 1 year. And Trish was asked to look into why. And there wind up being 3 major issues. One is drainage. In a lot of the tree pits, the soil just doesn't drain. And so you have, when the soil is wet, that drowns the tree because the roots have to breathe. And that's one issue. The second issue that Trish identified is dogs. The city is full of dogs. Dogs love trees, trees don't love dogs, and so that's the second issue. And then the third issue wound up being actually the sunlight. And there's especially where the buildings are tall, you have very little sunlight, and that winds up being an issue. So Trish did a lot of work looking at these issues, and in particular, she was able to show that putting a small fence around the tree has a measurable improvement, causes a measurable improvement of the tree lifetime. And then she wound up getting into a program which was looking also at using the tree pits as swales, and I think you were involved in this too. And so, there's a significant amount of water runoff. If the city's 90% paved, if it rains 1 centimeter, you actually wind up having, 9 centimeters of water that has to go somewhere. And one of the ideas has been to try to put it into these tree pits. And while that's great, if there's soil underneath, if there's no drainage, all you're doing is killing the tree, which is problematic. So Trish asked us if we could take the plant spike and use it to look at this problem. And so we did. So we did, there was a program that was run out of the Earth Institute in which they basically put a little sign on each of the tree fences and asked people to take a photo. You would scan the QR code, and then you would take a photo with the QR code scan, and then they would use that to analyze the condition of the tree and the tree pit. And so what we did is we basically made the Bluetooth version of our system also coordinate so that you could also get information about the drainage, the amount of sunlight, and the temperature, which temperature is actually not that mysterious at each of those sites. And to understand the tree health and also understand the effectiveness for stormwater. So we made the Bluetooth version, and that worked out pretty well. And then the next level above that was to really then ask questions like, okay, well, that tells us how good the soil is. How do we understand how the tree is doing? And so we added one more thing, which is, again, takes us from $6 maybe to the $200. I still have a dream, I know I do, to make a very low cost dendrometer. It's gonna happen. I think we can make one for $5, but let's see where we go there. And so we took the same system and we combined it with the dendrometer. The dendrometer is basically a belt you put around the tree, and it measures the size of the tree. And with the dendrometer, you can find out how much the tree has grown quantitatively. And you see it actually by the minute. When it rains, you can see the tree swell. It's amazing how granular that information is. And so we did a 1-year-long study where we put 6 of these on campus. We got a special permission from facilities. Actually, 5 of these are still there. One of them, they removed the tree to make that weird walkway. I know. But anyway, that's a whole different story. And so there we were able to then correlate the actual condition of the tree through the dendrometer, the soil, the condition, the drainage, and the other components. And the other big change that we did is instead of using Bluetooth for that, we used LoRa. And I don't know if there's been any installation of LoRa here on campus, but we're very fortunate at Columbia that, thanks to Cosmos and some work that's been done by some of my colleagues, we have a Radio Shack that's very high on campus, and with basically 2 LoRa bases, we're able to cover the entire campus. One of the bases is in my apartment, your old apartment, and that covers the southern end of the campus, and then the Cosmos base covers the northern end of the campus. And so with that 1 year, we were able to really look at tree growth, soil response, and actually make very specific recommendations for what needs to be done for each tree to improve its lifetime, its quality, its health, etc. And again, fast forwarding a little bit, our most recent work has been to try to see if we can get chemical information. And we recently, not that recently now, made an NPK sensor. And so this quantifies how many nutrients there are in the soil. And we haven't published the paper yet, but we now have a dog pee sensor, which we have made with a colleague at Barnard College who makes surface treatments that are enzymatically selective. And she's been able to make for us a system that, using the resistive ratiometric measurement, allows us to determine specifically whether there's urine that's gone into the treat pit, different and separate from water, or water that has redissolved old urine. Again, which gives you information saying, for example, this tree is fine, this tree needs a fence, trees elsewhere are going elsewhere. So, okay, not to harp too much on this, but I was hoping to give a little bit of a flavor of the type of work that we can do, at least on the smart city side, because we've done more with this, and we're always looking for new applications. But we've been able to use this also on our green roof. Trish Culligan was also responsible for our green roof. And green roofs are the absolute worst location for drainage because there's nowhere for the water to go. But you also need to have enough water. And so it's very common for the green roof to be either overwatered or underwater. And we were able to show by using just a single sensor that we could optimize and then harmonize how much water there is, and either put cover on or water the plants when they were dry. And hopefully we'll be able to do it again this year, but because the sensor is so inexpensive, we can put it in the park and just, I'll say forget about it. I mean, of course we want to communicate with it, but one of our local parks gets goats every year, or almost every year. Of course they didn't get it the one year because of COVID, where we were prepared to do the measurement. And they want to know if the soil is actually improving after the goats come and eat all of the weeds. And we're hopefully going to be able to do that this year. They're coming again for about 6 weeks later in the summer. So, okay, so we have this hardware, and again, we're always looking for new applications. And so I was speaking with a colleague at the medical center, and one of the things about the system is that it's very inexpensive. And so one of my colleagues has been asking this question. She's really interested in the behavior of wild rats. So rats, of course, are studied in the laboratory all the time, but the rats that you get in the lab are totally different from the rats in the wild. If you capture rats in the wild and you put 3 or 4 in a cage, after a few hours, there's only 1 rat left because they fight and they don't like to be together. So the rats that you get from the animal breeding for animals, they're totally different. And they really can't be used for behavioral studies the same way that wild rats can. So my colleague's idea, which is an interesting one, is to use the city as a laboratory. Because if you can't capture the rats, what you can do is you can catch the rats, implant them with some instrumentation, then set them free. And she actually has a permit to do this, which is interesting. The problem is the first time she did this, the animal was killed within a few hours by a raccoon. Rats, unfortunately, are not the top of the food chain. So there's the raccoons, and then there are also the hawks. We have several hawks on campus, and actually it's near the medical center where she can do this. And so it was very expensive for her because she never recovered the hardware that she had. So she asked us, well, if you can make a LoRa thing for $10, can you make a rat implant for $10? And the answer is yes. And so we were able to make the system, and in particular, we did 2 things for her. One is, of course, it's totally implanted, but we also were able to show that by using a flex circuit board, that the animal heals 1 day faster. And it's actually, after you release the animal, it has, with a rigid circuit board, it has about a day recovery time, and that's the time where they're vulnerable. And with a flexible circuit board, the recovery time is reduced, and so the animal then is able to run, and we were able to work with that, and we're hoping that that'll also be used. Actually, we're working with the Global Center in Kenya because they also want to do the same thing with storks in Kenya, but there it's much easier because you use a hot glue gun and you stick it on the back of a stork. But again, same hardware, but you can answer similar questions, and there they're really interested also, again, the migration of animals in and out of the trash dumps and in and out of the community. So in this first part, I just want to show, even very simple hardware, $1, $2, $3, $5 can be used to find some useful things out about the environment. And part of the value here is having the very low cost hardware, because you can then distribute it in the field, get your answers, and I mean, of course, you don't want to leave trash out there, but it's not a catastrophe if you lose the hardware pieces, whether it's in the rats where they run away or get killed, or in the soil, in the plants. It's okay if someone comes, picks it up, or something happens to it. And you can also use modern integrated electronics to really push the cost down. And I think I showed a couple of tricks that we've developed, one of which is to use the circuit board as a connector. A second is to have a board integrated antenna, which again reduces the cost because the antenna is effectively free. And the third is to use the circuit board elements as the sensors, which we do for both the chemical sensor with the interdigitated fingers and the capacitance sensor, which then eliminates the need for a lot of post-processing and lets it scale. So that's one thing I just wanted to touch on and to see if there's any interest in collaboration or integration. And just a couple papers, and just let me know if you want a copy. The second thing that I've worked on is also Internet of Things type project, looking specifically at steam heat. Of course, I know the Columbia people have, but has anyone else here lived in a steam heated building?
It's not a thing in Greece.
Yeah, Greece, you don't really need heat at all, right? I say that, of course, I've been here in the winter. You need a little heat. But I know steam heat is very popular in the northeastern United States and in like the Soviet bloc, Central and Eastern Europe, as it is. So New York City, steam heat is in about 2/3 of the buildings. So there was a period of time where it was in fashion, and that happened to be when most of New York City was built. And for everybody that's lived, I don't know, Bianca, how would you describe steam heated buildings? There you go, exactly. They're extremely hot. It'll be the coldest day of the winter, and you walk around New York City, and people's windows are open. It's like, it's insane. And everyone's uncomfortable, everyone's complaining, and of course the landlords are complaining too, because everyone's just dumping all the heat out of the window. And there are a number of thermodynamic reasons why, but I have a student, Marshall Cox, and he has a twin brother. So Marshall got his PhD in my group, not on radiators. He was doing photovoltaics for energy harvesting, so it's sort of related, but sort of not related. But he has a twin brother who's a professional dancer, and his twin brother got a part in this play, which closed after 2 or 3 months. It was a little bit unfortunate. But during that time, because the play didn't run that long, he stayed in Marshall's apartment and complained to Marshall every single day. And he was like, why is it so hot? Like, what can you do? And the first couple of days, Marshall just shrugged and whatever, and then Marshall spoke with me about it, and we had an idea, which is that, he lived in a Columbia University-owned apartment, so we weren't going to change the plumbing. But, the basic idea people usually have is to throw a blanket on top of the radiator, and that helps. That brings the temperature down. But the goal is not to be cold either. And so the one change we made is we have an insulation, and we also added a fan. So this fan blows air from the room in when you want heat, and when that happens, the steam condenses, it sends a condensate down, and then you can get some heat out into the room. And so, this worked the first day. It was really straightforward, it seemed. And anyway, and so basically Marshall, after this, decided that he was not going to have a career in electronics, but instead that he was going to do this. He started a company which is now called Kelvin, which makes this system. And the one trick about the system is it's not enough to just control each radiator. You also have to decide when you're going to fire the boiler, which is actually more complicated than I ever thought it would be. But anyway, but that system, basically every radiator reports back to a central server. That central server makes that decision. It also can make decisions based on the cost of gas. If the utilities have incentives, sometimes, not that often in New York, to delay when you start, or to heat up the unit early, and works that way. And anyway, and so this system now is in production, which is nice, and it allows for a retrofit of a building. It improves the energy efficiency, improves the comfort, but also the hope is that as time goes forward, it'll also allow for more electrification of buildings, because one of the challenges in New York, at least, is there's just not enough. Everyone says that they want electrification, 100% electrification, and that sounds great until you realize there's nowhere near enough service to electrically heat every building. And so at least for the next 30 or 40 years, we need some kind of hybrid structure where we, as efficiently as possible, use electric energy, but also, where necessary, fill in with fossil fuels. I won't get into this too much because I'm out of time, but you know, it's a nice system, and they have a very nice sort of design for it. And the biggest benefit that many people report is that normally the radiator just takes up space, but now you can actually put plants on top of the radiator next to the window because it doesn't bake the plants anymore. So that's like something people really like. And there's about 45,000 of these so far that have been deployed. And so, you know, it's a pretty big problem in certain markets. And, you know, we'll see. And I guess Greece doesn't have a heating problem, but I think we can apply some of the same techniques for cooling, which I think is a really interesting direction. Okay, so I hope I've convinced you that Internet of Things technologies, even though some of them are not that complicated, they provide, I think, an opportunity for low-cost deployment of sensors. And if we're creative about how we use them, we can use those sensors. In the case of the Radiator Lab system, it's just temperature, occupancy, and essentially the central control signal going through. And in the case of the plant spike, again, it's relatively simple, but allows us to improve the probability that a plant, you know, tree, which is multiple $1,000 investment, can survive. And so I think that there are a lot of those opportunities, but the real key is understanding the market and the underlying incumbent technologies. So with that, I just want to thank you for your attention and happy to answer any questions.
Excellent presentation from Zografou. Question: these humidity sensors, how deep can you embed them in soil? For example, can you put them down a few meters?
Yeah. So that's a great question, and that's actually the first reason we moved to LoRa, because LoRa is at a lower frequency, and LoRa in wet soil can go not a few meters, maybe 1 meter, maybe depending on how wet it is, maybe even less. However, if we can have a tether, then you can do anything you want. So there's a question of how deep it can go, and the radio can see the sky. But I mean, if we can connect with a very fine wire, you can go as deep as you like. And we did some work, actually, one of the theses that Trish's student did is to replace the standard infiltration measurement with just 2 of these sensors. And then you dump a bucket of water and you see what the pattern looks like in terms of the hydration going up and down as a way to get a direct measurement. And he showed that it's as good as the infiltrometer that he was previously using.
It is intriguing because of the low cost. Because if you start embedding this, let's say 1, 2, 3, 4, 5 meters and so on, you should be able to detect the level of water table.
Oh yeah, absolutely. And again, there's no contact galvanically, so it doesn't corrode. The whole thing is insulated. So yeah, absolutely. Oh, the water table would be easy because the difference in capacitance is enormous. You know, water has a dielectric constant of 80, so absolutely. Yeah, that'd be great.
I'm curious what the rat sensor, the range for communication, and then how often, also accuracy of position.
Oh, the position accuracy is terrible because there we were using a triangulation which tries, I say tries very generously, to use the power at the various base stations. So at the medical center, we have, so the, right, this is TMI. The permit allows to capture and release rats in 2 places. One is a trailer in Central Park, which is a pain in the neck, and the other is the loading dock, which has the trash dumpsters at the Psychiatric Institute. So there, the range is actually pretty good because rats don't go that far and they don't burrow that deep. But the range for LoRa, open sky is supposed to be 6 kilometers. In reality, we also don't run the battery at the radio at full. So it's maybe 1 kilometer, 1.5 kilometers. But it depends on where they are under and whether it's raining. That's the first thing. In terms of the triangulation, it's terrible. We have a paper where this is what you do during COVID. We sent, we had hired some undergrads for the summer, so we just had them roam around the city and do essentially like an accuracy of the triangulation, and it's really bad. So we were hoping to put 2 or 3 more antennas up at the medical center, but that got gnarled in a bunch of political issues because anyway, we don't have to get into it. There was going to be like a Cosmos 2 up there, and it fell apart. And so we weren't able to we only had 3 antennas. If we had like 5 or 6, I think it'd be better. But I wouldn't put too much stock right now in the geolocation using the LoRa system. Yeah, but we do have that thing where the students just roamed, they roamed around the city. Both of them got into Columbia afterwards. We could, it's just GPS is very power hungry, that's all. In principle you can, and actually we did that for the stork project, but storks, so with animals there's a general guideline that you can only get about 10% of the weight of the animal as an extra add-on, and so in Nairobi there's this really interesting problem where there's a huge trash dump next to the city. There are trash pickers who live in the dump, and then the storks go from the forest to the trash dump. And there's this concern, and there's a project by the Smithsonian that we collaborate with. There's a concern that the zoonotic diseases from the forest go into the trash dump through the storks, and then the storks give it to the people, and then the people mix in the city. There, we can put GPS because we can put a much heavier battery, and you can do much more. The rats, the amount of mass we have to play with is not that big, and we wind up burning it almost all in the battery. The other things with the rats, the storks, they see the sky, easy. The rats, we found you can realistically only put stuff in the belly on the bottom, and there's some reasons for that. On the back, the spine, skin, like if you separate that fascia, the animals don't recover well. And so that means the whole body blocks. And getting GPS, at least with our calculations, is difficult, even if they were outside. I don't know. We have a new project. So the only one, so I showed you, we've done a lot of work on ammonia, and we have a different sensor for which can do CO2 and methane. I don't know about general air quality. I'd have to think about how we would do that. Do you want to look at total VOC we can do using the methane sensor? You can actually re-engineer that. I didn't show how that works. There we have like a high frequency resonator. Yeah, or we can call it a metric sensor. There's some that people propose. I don't know. It's all a question of whether you have enough power and exposure. But yeah, I don't see why not.
I wanted to ask you, so these are going to be very cheap, $1 sensors, like fertilizer, or cost of the fertilizer.
Exactly.
And, but then we are going to get tens of billions of them.
Yep.
So for the business, for this to be, since it's going to be a commodity essentially, does this create a pollution problem essentially? And maybe organic electronics could be help here. Are they mature enough to do the functionality of organic electronics?
Yeah, absolutely. So you ask a great question. We actually have a new project on how to deal with this. And so the one thing that we've been able to do is first replace the plastics that are in the circuit board with nanocrystalline cellulose. Nanocrystalline cellulose has almost the performance of plastic sheet, but is biodegradable. And so that's the first part. So that gets the circuit board part. Now the electronics, I love organics. I grew up with organics, and there's certain things they can do for us, but they don't make good radios. But that said, you can have like a low silicon content. The total, you have to ask what the budget is for trash. Like silicon itself isn't really environmentally harmful. So I haven't done this work, but others have shown that you can do like a bare chip bonding and then go from there. And so I think with the nanocellulose substrate as one direction, there's other groups that have different things. Some groups have been using silk fibronate, which I haven't gotten into, but that also has a reasonably good performance. And then if you can do bare silicon, then it's just a little bit of metal, and metal itself generally is environmentally acceptable if it's not copper. Copper, unfortunately, is considered to be a persistent environmental hazard. So silver, I think, is kind of the direction we're going. But you're absolutely right. But we've shown that you can print the antenna and make everything on at least a degradable substrate, and then you have to ask questions. I mean, not perfect yet, but I think you can make the whole thing resorbable and environmentally acceptable.
What will be the cost? Let's say the bottleneck. I mean, if you have so cheap IoT sensors, etc., in the value chain for smart systems, etc., what would be the expensive thing? Would be the communication? Would it be the processing of it? I mean, where the value goes if this becomes commodity?
So in most of my experience, the biggest expense is the people that are out there to deploy the system. Like for the Kelvin, the Radiolab system, it doesn't matter how cheap you make the whole system. Once you need 4 guys to go there, carry it up the stairs.
You can just throw them, right? I mean, if you have an expensive.
Oh, how I wish. Oh, sure, but even that is not. Personnel is never free. That winds up. I think that might be one of the bigger cost points. But yeah, we'll have to see. I mean, but we need to think of more. I mean, I love IoT stuff. I think it's cool, but particularly as we think about collaboration. The key is to find those like high value applications where we can use the technology to answer like a real pain point. Like the tree and the soil drainage is like, it's like a tangible thing. The city spends millions of dollars a year on trees. If we can rescue 5% of those trees, that's worth it for the city. And that's like a real reason to do it. So it's worth like tuning up in the applications. What's the value proposition? And then we'll be able to actually answer that question. Because in some applications, for example, you need a 10-year battery life. That's much more. That's no longer a $1. That might be a $3 or maybe.
But you have this wake up, sleep and wake up protocol. So the battery is probably not a problem, right? I mean,
yeah, we get 2 years for the current version of the plant spike with a extremely cheap with a 2035 battery. But again, if you want more information, if you want GPS, all these other things, you know.
By the way, how much would it cost the cheapest?
The cost it's like $10 or so for the electronics after you pay for the antenna. The antenna is not that expensive, but it's a surprising amount of signal processing, and it's pretty energy intensive. So, yeah.
Another question? Very interesting stuff.
All right.
Thank you very much.
Thank you very much.
Next presentation is Victoria Morphopoulos. Victoria.
Thank you very much for inviting me to this very interesting let's say, seminar. Is it a seminar or is it an opening of future collaboration? Thank you, Professor Varvarigos, Professor Deodatis. It's a great pleasure to be with you today. And before starting this presentation, I would like to welcome our colleagues from Columbia University to Athens. Enjoy Athens, even very hot. And I would like to invite you as well to submit, perhaps, an article of your presentation to the Technical Annals yesterday at the Technical Chamber of Greek Engineers, and we are a lot, 100,000 and more, even 110, I think, today. Technical Annals have actually inaugurated the first volume of 10 issues, and among them, the 9th one is being dedicated to this issue. And that's the reason I would like to invite you to submit your article there. This special issue is being edited by Professor George Theodatis from Columbia, Professor Evangelos Apoutzakis from NTUA, and Professor Kyriakos Lambropoulos as well. I'm the chief editor, and that's the reason I'm extending this invitation to you. Coming back to our issue, we are working on the assessment of the resilience and sustainability of infrastructure in a changing climate by non-destructive testing. This is a work we present with Kyriakos Lambropoulos concerning many experiences on research and education as well, focusing on materials. As it is known, we were not expecting the climate change in order to put on the finger on the problem, and the problem has been caused by weathering, by aging of materials, and by overuse of the structures. And the actual fact is that we are at a critical point of time. I mean the built environment of today, which has been developed within the two world wars and was shaped in its today image after the Second World War, is now facing the end of its lifetime. 70 years after construction, we are having to do with civil infrastructures that, due to the weathering, the aging, the lack of maintenance, and their intensive overuse according to the standards taken into consideration for their design, are today facing a lifespan significantly shorter than the one that was estimated. Of course, this is shaping the actual reality of construction developments, and as Professor Theodatis asked before, we cannot, of course, conclude for what is the economic outcome of the damage of the climate change, but we can tell for sure that the 40% of construction activities in Europe, a little bit higher in Greece, is guided to the renovation of buildings. This doesn't mean cultural heritage, it means aged buildings. Of course, this is the reason that in Greece we are dealing with the issues of the quality of the built environment with very recent established laws like the law of 2017, 2024, which are in a way developing institutions for the quality control, like for instance the construction evaluators, the building evaluators, and of course some mechanisms to do that, which are dealing with the Technical Chamber of Greece, the various syndicates of architects, civil engineers, etc., and concern actually the permits, the the control of implementation of plans for public areas, for environment, for unauthorized buildings, observatory for the built environment, and others. These are not connected to the research and the know-how level of Greek scientific community and the Greek universities. Especially today, due to the social and economic crisis, we are facing a prevalent crisis in the built environment, and we are in front of the needs to consider all these parameters in a holistic approach. Of course, from our point of view, materials are the ones that embody this change of environment, because till the age of climate crisis, we were talking about weathering. Today, we are speaking about climate crisis. Which is the difference? The difference is that we have intensified conditions for weathering that overcome the normal procedures of aging of materials that usually are taking us from decay phenomena on the level of materials to the pathology of structures. So there is a quality change. We are going through climate crisis to this direction, and that's the reason that we need to evaluate and classify the values of critical parameters in order to interrelate this phenomena at the interface of environment, materials, and structures. Of course, considering the parameter of design. That means we are in front of interdisciplinary phenomena, not multidisciplinary anymore. And we cannot have as a reference level a discrete scientific specification, a discipline. We have to go interdisciplinary. That's why the optimization of the methodology to study this phenomena concerns the need for the holistic framework that will, first of all, identify the data of materials decay, even destruction, with the level of the structure, the pathology of the structure. That is an issue on which, with Professor Deodatis 30 years ago at Princeton, we were working at the model of earthquake vulnerability and strengthening of Hagia Sophia in Istanbul, in many important religious monuments in Latin America and elsewhere. So the utilization of non-destructive testing are a level of in situ investigation, because they permit us to study in real scale and real time the phenomena and interrelate in within time series what is happening. Of course, we are going from understanding the system, characterizing materials, documenting problems, analyzing risk analysis until the mapping of the decay, and finally estimating the need for intervention. I mean, the risk, which is the risk that necessitates the necessity index to intervene. Then we design, we plan the intervention, and then we monitor the quality of the intervention, the results of the intervention, and following step is to monitor the new state-of-the-art of the building in the environment. That is the holistic study of interaction between environment and materials, but always on the level of structures. You cannot make an abstract approach. That means that we are focusing on working with our data on georeference points of the structure in order to represent on the level of the structure what is happening with the mechanisms interacting between environment and materials. We are using advanced computational methods, like, for instance, the old and good finite element model, but in this way it is more dynamic and more precise. And of course, speaking of intensive environmental stresses and conditions, we need to simulate what is happening on the level of the site with what could be predicted at the level of laboratory. That means we know we are working with stochastic models, but the need to an anchorage to the deterministic ones is necessary in order to understand the mechanisms and go further. The fusion mechanisms is the mechanism of uploading the various disciplines data, here in that case the entities data, on the 3D models. Concerning some applications, I could speak for the case of integrated diagnosis, evaluation, and assessment of the durability and load-bearing capacity of bridges by non-destructive methods. This methodology has been produced by a group of engineers from NTUA, from the material science, from civil engineering, from serving engineering, and from architecture, as you might see here. And it is very important. Today, we are, for instance, using sensors to study the deformations of the bridge, dimensional differences. But what is the meaning? What are the semantics of these sensors applications if we don't know what is the actual deformation and how it is produced on a certain bridge, which has a certain construction technique and certain materials, some load-bearing capacity, and some uses foreseen for that. So in this case, you can see here the multi-channel ground-penetrating radar survey of the bridge deck for 3D prospection of the internal structure of the bridge. That means we are reproducing the deformation in order to study with the structural models where we have to assess the vulnerability and to redesign, structurally redesign the structure. Historical bridges like the Plaka Bridge in Arachthos, for which National Technical University has worked out with an interdisciplinary team on the same approach. With the ground-penetrating radar survey, we have disclosed all the construction techniques and the history of maintenance and interventions to the historic bridge in a way that it allowed for the redesign and for the rehabilitation of the bridge. In the same way, we have worked out for, in the former Ellinikon airport, where a huge governmental project is now taking place, in order to assess and evaluate the demolition impact before starting demolition, in order to protect monuments and the acoustic areas around it. Non-destructive testing was providing data, and decision-making tools were compiled from this data in order, first of all, to document underground water supply networks and foundation structures, and on the other level, something very innovative concerning the landscape. It was a former airport, that means air pollution and infection as well. And in order to take some statistically semantic samples, but with economy, and in a very brief way of study, we had used the electrical resistance tomography, where major peaks were provided, and we had examined these samples to conclude for environmental pollution and infection, and to go on with the plans to recover the site. The same, it was very important for the demolition to simulate demolition, and by sensors that were measuring the performance of the structures according to these frequencies, we had assessed and evaluated what the demolition frequencies should be in order not to harm the area. In this way, with non-destructive testing, we had assessed and evaluated the pavement sections of the Athens State Airport at its renewal in 2004 with infrared thermography to investigate distortion peaks, and with ground penetrating radar to study in depth whether the intervention should go in depth or on the surface. The same concerning the maintenance of Attikometro, which is a railway infrastructure for the city and is very important for preventive maintenance. Apart from the well-known techniques, we have used the infrared thermography and, of course, the digital the digital video microscopy in order to search out not only the cracking, which was in a process of development, but in order to discern active paths of cracks before they were developed and before they were presented on the surface. That was a major step for preventive maintenance, which was useful as well for the maintenance of the railway line, with a rail defect warning system, which was developed after pattern recognition, classification, and of course the warning. And at the Hellenic Railways organization, where the metal bridges are of interest, we have started working with eddy currents, which is the usual approach, but as well as passive infrared thermography, video microscopy, laser scanner, and ground penetrating radar, in order to disclose and, of course, propose how to avoid major deformation problems. I don't want to go to details. I would like to say that an integrated documentation management for the diagnostic study of a whole city, like the historic city of Rhodes, the medieval city of Rhodes, through the non-destructive testing, permitted us to suggest advanced management by entities for the environment in order to protect historic structures. And in the case of the rehabilitation of the Holy Edicule in Jerusalem, non-destructive testing was permitting us on the 3D level to estimate structural analysis with precision and to rehabilitate on time the structure using a big data compilation which we evaluated by AI according to the data from the remote data acquisition by sensors, which was very important, an integral approach of sensors, but has been now seized. Anyway, an innovative multi-layered data management, which we worked out for the case of this monument, permitted us to work out on interrelational databases, and it gave to us the possibility through the content-based management to develop semantic data integration and to approach usability of digital-driven preservation of cultural heritage. Of course, entities are essential for modern and historical structures and infrastructures, and a vast interdisciplinarity with architects and surveillance engineers could permit us, as in these cases in European projects, to work for a complementary and fused elaboration of data in BEAM, HBeam, and other augmented reality systems to document and to manage built environment. That means that we could, if we are joining our forces in research directives, that we could compile data and we could interrelate data to sustain the prospection of sustainability. Innovation is both a challenge and a solution in these cases, and we have to work towards this. In our case, we are working with green materials as well, considering compatibility, which is a dimension very important for us, because incompatibility of materials, along with intensified environmental stresses, might develop internal structural stresses and trigger problems. AI is giving very important tools for decision making. some of our data elaborated with these tools, I hope will be presented by Professor Goulamis tomorrow. What I would like to say closing this presentation is that we have to go a step further. The two universities' collaboration seems that is very interesting and very promising, but it has to be interdisciplinary. Thank you very much.
Questions? You have looked at the very different cases, starting from San Sofia, Holy, etc., all modern bridges, So, the data that you have developed, that you have obtained for these very different cases, is it do you have a model? I mean, is it useful to combine this data in a single training, let's say, set for AI applications, or is it better to use separately, fine-tune on separate for each of these applications, use separate data and not merge it? In which case, a model may change the other model, may make the other model.
Yes, very interesting question. I should answer by saying that each problem requires a unique approach, but the major issue is can we standardize the assessment that we are gaining from the NDTs? No, we cannot standardize the assessment because it is one problem, one solution. But what we can standardize are the procedures. And in the project Evlogon, which you know very well, an emblematic project where we are trying to utilize unique interdisciplinary approaches in emblematic monuments. What we are looking for is to standardize the procedures from monuments to infrastructures in a way that architectural, structural study, the material study, the supervising study, the management study, the informatics management of data will all serve for the holistic setting of the project and solution of the project. Thank you. Yes?
Very interesting data is very crucial key element in
modeling, simulation, and in AI. And the data collection process, in your opinion, can we standardize this process? Because it's actually a data collection, or it's something more. It's a protocol. It's like the medicine, which, for example, if we make a medical doctor a clinical trial, first, from 1 year, he surveyed the clinical data collection process. So the data, the whole procedures, from the architecture to from the plan to the architecture, the whole data we measure during, it's just as a genius, just data or something more. And this we need to standardize in some way.
Yes, as I said to Professor Barbarikos, we need to standardize the procedures. But concerning the measurements, even though we cannot standardize the measurements from the point of view of their semantics, we can standardize the measurements as measurements. That means we have and we need to give protocols for the measurements in order to get meaningful data for elaboration. But only meaningful data means nothing if you do not proceed with the various disciplines and concrete procedures that will fuse the data in order to accomplish the holistic approach that is required. Professor Ambrogio.
Yes, the answer is depends. Depends on the technique. As you've seen in previous presentations, there are some data
like humidity. Temperature is a number. So you can collect the numbers and you can see the trends and patterns and so on. But how do you manage infrared thermograph? It's an image. If you look at it as an image alone, okay, you can do image processing, you can get some tracks, that's about it. But then you have to realize what the image represents. It's an image of a surface that reflects all the phenomena behind this wall. The same with other techniques like a georadar. You get another image, then you see some layers, but the beautiful information is not the layers per se, but what these represent to the structure, and so on. You have an ERT, electric tomography, you have tomography, you have some very nice colors. What do these represent? What kind of information, semantics or whatever you can say about this is? So the answer is, again, it depends. It depends on the technique and what you can get from it, you apply it. And why you apply the technique. So Professor Makul is correct. It's about you standardize the interpretation, let's say, not the actual implementation of the technique. Some of the techniques are already standardized. Ultrasonic, for example, it's very common. But you need to standardize and you have to focus mostly on the interpretation in relation to whatever you are studying.
Yes. But and actually the temperature, I think that, for example, let's focus from the medicine point of view. Okay. Yes. If for example I measure my temperature, it means nothing. But if I measure the temperature with respect to something, I don't know, with a control procedure against something else, maybe this statistically means something. So maybe we need to somehow make comparative statistical measurements.
Or interrelated.
Or interrelated. For example, just a measure means nothing. Exactly. But if, for example, you have a statistical group, okay, and another control group with the same statistics, but only one variable is going to be changed.
Because you are right, we need protocols. For instance, if we are performing digital image processing on decay patterns on masonry, historic masonries, without taking into consideration the porous structure of these building materials, we are out of any interpretation. So this is a very precise answer, and there are very many following, considering each technique.
Very, very quick question. Thank you for your excellent presentation. I remember in the 1990s, we were using ground-penetrating radar for the Hagia Sophia. Since then, has there been any improvement in the technology of ground-penetrating radar, especially as far as the depth and the accuracy is concerned? Because I have not followed the area at all.
The accuracy is important, and that's why I presented the multi-channel ground-penetrating radar, which is the last outcome of high tech in this field, coming from Sweden. And this permits us to work with very precise representations of the deformations at thin and depth levels on the ground. So this is giving us a range of deformations that would be meaningful in order to assess and evaluate structurally what is happening with the bridge, for instance.
I think also the US infrastructure also has problems as, important problems as not only Greek infrastructure, right?
That's for sure. I was speaking of our experience. Thank you so much.
Thank you, Tonya.
Ευχαριστώ πολύ. Αυτό δουλεύει. Λοιπόν, μπρος πίσω. Μισό λεπτό να το πάω.
Αλλά από εδώ, κάτω πάνω.
Ωραία.
Και αν θέλετε να δείξετε τίποτα με λέιζερ, το φωτάκι.
Ωραία.
Το άλλο δεν το πειράζει καθόλου. Δηλαδή είναι πάνω κάτω και φως.
Okay. Hello everyone, I know it's late. I will try to make it as simple as possible, and I would try also to make some connections for potential collaborations with the NTUA faculty. So this is, if it moved, move this way. This is part of the group we're working at Columbia, including colleagues, PhD students, master students, as well as undergraduate students. So this is a collective effort. So in the beginning of the day today, we talked about climate change. So let me show you a couple of figures here. So this is the evolution of the global surface temperature. So this is some kind of an average over the entire planet, starting from 1880 until today. And without climate change, this should have been the evolution. This is natural drivers only. Of course, it's an estimate. Instead, this is the evolution of the global temperature, and the red line is a 20-year moving average. Very clearly, there is something going on here. Global sea level rise. There have been a lot of people saying, okay, sea level rise has always been happening, it's a straight line, it's not due to climate change. If you can clearly see here, I should have drawn a straight line. Straight line would have been something like this. It's not a straight line anymore. It's clearly non-linear. Of course, sea level rise is not uniform over the planet, it changes from place to place, a lot of different reasons for this, but it is very, very important. Just for the United States, around 1/3 of the population lives close to coastal areas, and similar values apply for the rest of the world. And on top of that, sea level rise makes coastal storms much more destructive. Tropical cyclones and climate change, you see again a plot of the number of very intense tropical cyclones in the Atlantic region hitting the United States, and Central America, and these are only category 4 and 5 hurricanes, again from 1980 until today. And you clearly see here an increase, although there is not currently a consensus about how climate change will affect hurricanes in general. Most probably we'll see an increase in intense rainfall, increased coastal flooding from higher storm surges, and they will become more intense in general. Since some of the emphasis today is going to be on the effects of hurricanes on the coastal infrastructure, there are 3 mechanisms creating damage. The storm surge. Storm surge is not very well known in Greece because it's not so common in the Mediterranean Sea, but as a hurricane propagates and reaches the coastline, it pushes the water literally, so you have an increase in the height of water. It's like a slow-moving tsunami, let's say, but it's an increase in the height of the water that can be very, very significant, that pushes inland. On top of that, we have rainfall-induced flooding, and these two can combine in some cases. And of course, if you have a hurricane, you can have wind damage. This results in loss of life, unfortunately, damage to our infrastructure, power outages, and then of course, after the hurricane, you might have standing water that can contribute to insect-borne diseases, crowded shelters for evacuees, increase the risk of disease, and so on. This is an important plot, and this is established, if I can see here, by the National Oceanic and Atmospheric Administration in the United States. And these are billion-dollar weather-related events in the United States. So these are events that produce damage over $1 billion. If it's 900 million, it's not included here. And the different colors have different types of extreme events. With the green, it is severe storm counts, but there are all kinds of events, flooding from rainfall, freezes, wildfires, winter storms, and so on. And it is very, very clear that there is a dramatic increase in the losses. So I believe I have convinced you that there is climate change happening and that this has a significant effect on the losses to the infrastructure. Very, very quickly, the example in New York City. We had a hurricane hitting the city in 2012. These are some views of New York City. The Rockaway Peninsula is here. This is a car tunnel. I advanced, sorry, I cannot go, yeah. This is a car tunnel. This is a subway station, metro station, and this is a view of Manhattan. So, same areas. This area, the Rockaways, was, was flooded. This is flooding of the car tunnel all the way to the ceiling, flooding of the subway station, significant blackouts throughout the entire area, $65 billion in damage. This is not inflation adjusted. Out of this, 19 billion in New York City, unfortunately, very significant loss of life. Over 5 million people without power in the northeastern United States. And these are the most catastrophic, these are now inflation adjusted. This is why you see Sandy went up to $88.5 million. But what is interesting, most of them are very recent events. Professor Sobel mentioned, of course, and this is a significant reason, that there is much more infrastructure in areas that are susceptible to these events. But we are talking here about a period of around 10 years, 2017 to today, a lot of events that are really dramatically catastrophic. So let's concentrate in New York City. This is predicted sea level rise in New York City. The blue is the range. These are actual measurements. This is by a group at Columbia with Radley Horton in this group. And of course, as I mentioned, coastal flooding is going to be worse with sea level rise, because on top of the sea level rise, you will have the actual storm surge. This is a plot of a study we did for New York City 2 years before Hurricane Sandy. Sorry, New York State. So New York State asked us, consider a few different flooding scenarios, 50-year storm, 100-year storm, I think 200-year storm, and what are going to be the effects on the built infrastructure. This is Lower Manhattan, this is Brooklyn here, and the 100-year event, we predicted flooding in all these subway lines connecting Brooklyn and Manhattan, as well as the car tunnels. Nothing was done despite our dire predictions. I'm not accusing any of the agencies in New York City. They said, we don't have money, and this was the case. I mean, everybody living in New York City knows that there is no surplus in the New York City subway that can be used for these major improvements. And this is not a problem with New York City, by the way. People think that the Dutch are acting preemptively to protect their country, which is a matter of life and death. I mean, significant part of the Netherlands is below sea level. The answer is no. They acted exactly like everyone else in the world. On the left, you see Cornelius Lely, civil engineer. He tried very, very hard to convince the Dutch to take action to protect the northern part of the country, the Zuiderzee, against storms coming from the North Sea. He was unsuccessful. Then he said, okay, what if I become a politician? He became a politician. He became the Minister of Public Works in the Netherlands. Was he able to convince the Dutch Parliament? No. There was a major flood during World War I in 1916, and then immediately after the war, they implemented Lely's plan. And you might say, okay, the Dutch learned their lesson. The answer is no. Lely, who was at the time a national hero, selected Johan van Veen to establish a plan to reinforce the southern part of the Netherlands. Did they do something? No. There was another major storm in 1953, and again, this is when they decided to implement Van Veen's plan. So this is universal. There is no country that is going to spend billions of dollars to reinforce an area against a natural disaster like this. So New York City, we are now 13 now years, sorry for the typo, this was from last year, the slide, after Hurricane Sandy. So the New York City metropolitan area is mostly preparing for a repetition of Hurricane Sandy, meaning we are reinforcing parts of the city that flooded during Hurricane Sandy. This is the part of the city that flooded during Hurricane Sandy. This is Manhattan, this is New Jersey, Brooklyn, Queens. Whatever is light yellow was flooded. Hurricane Sandy occurred at high tide. Keep in mind, in New York City, high tide to lower tide has a difference of around 2 meters. It's like Halkida here. It's not that bad in New York City. Halkida is more than 2 meters, I believe. So this is the flooding. Hurricane Sandy storm surge hits during high tide. If Sandy had hit at low tide, this would have been the flooding, really minimal, because everything would have been 2 meters below. And you might say, okay, they're reinforcing for the worst case scenario. Yes, that's fine. But have a look at the northern part of New York City. So this is Manhattan, this is the Bronx, this is Queens. The dark blue is the area that flooded during Hurricane Sandy. Very little, the dark blue. And forget about this, this is a mistake. This is LaGuardia Airport, it did not flood. I have not corrected this. But this part of the city was at low tide at that time. If it were at high tide, the light blue area would have flooded dramatically more. But New York City is doing nothing for this part of the city because it did not flood during Hurricane Sandy. Anyway, what we have done is to develop a general methodological framework that, given a prescribed budget over a period of time, let's say we have $10 billion to reinforce an area over the next 50 years. And you can run this with different budgets, establish the optimal adaptation measures. And by optimal, we mean maximum reduction in losses over this period of time compared to the case of doing nothing. If you do nothing, you will have multiple storms, you will accumulate some damage. If you have a budget, the optimal use of your budget is the maximum reduction in these losses in the case you will do nothing. And of course, you have to account for every possible kind of hurricane or winter storm approaching the city from different angles, different timings, with the tidal cycle, sea level rise, and a lot of other uncertainties. And eventually, the optimal strategy is going to involve a combination of protective measures implemented at different locations and at different times. And of course, you have to take into account stakeholder feedback. These people know a lot of stuff that we academicians don't know. And I will try to go fast here. We need probabilistic models for the storm occurrence and intensity. And as Professor Sobel mentioned, you can either have data, you can have synthetics, simulations of storms, you can combine these effects. In any case, you have to separate between warm season and cold season because the underlying mechanisms are different. This is an interesting record. These are all the big storms in New York City over around 100 years. Red circles are warm season storms, blue circles are cold season. This is Hurricane Sandy in 2012. You see it's around 2.75 meters high. This is the pure storm surge. And we had a probabilistic model fitted to the data were fit very, very nicely with a beta distribution, except of the last 5, 6 data points corresponding in major hurricanes, and obviously there is a different physical model behind these data points. And we did the following as an idea. We fitted a different, this is the beta distribution. So for these points, we fitted both an exponential and the type 3 distribution, asymptotic distribution, and we assumed an upper bound. This way, we avoid the possibility of a distribution with an open right tail that goes to plus infinity and might create unrealistically high storm surges. So we consulted with our colleagues in the Goddard Institute for Space Studies, and they told us try 5 meters as the upper bound. Keep in mind now Hurricane Sandy is around 2.7 meters. So this is a significantly higher upper bound. So this is an idea for the probability distribution of the maximum storm surge height. Any other model can be used in our methodology. This is the same in a much easier to understand plot. It's a function of the return period. This is the surge height, warm season. This is Hurricane Sandy. 100, 1000, logarithmic scale. So this is the return period according to our calculations of Hurricane Sandy. And we assumed, it's not here, we assumed the Poisson distribution for the occurrence. Of course, there's a big unanswered question. Everything so far assumes stationarity. Now climate is changing, all these frequencies, intensities will change. To the best of my knowledge, there is no consensus about a new probability distribution. If it becomes available, it's very easy to implement it in our model. These are estimates of sea level rise in New York City, and look at the uncertainty, 2100. This is the low estimate, lower percentile, 38 centimeters, almost 2 meters for the high percentile. You realize the level of uncertainty here. And then there are a lot of different things that we can do. Generally, 3 categories: nature-based measures, restoration of wetlands, sand dunes, oyster reefs, and so on, engineered measures, barriers, seawalls, raising the infrastructure. This is within New York City. After Hurricane Sandy, they established watertight closings to every ventilation openings, every station opening, and of course, insurance, and the most controversial measure of all, strategic retreat. There are some communities that are already flooded multiple times per year with the increase in sea level rise and intensity of storms. Eventually they will have to move at higher ground. We're not saying this is going to happen tomorrow or in 5 years. You tell the community, after 20 years, you might have to consider moving to higher grounds. So the methodology, I'm not going to go over it. It's an iterative methodology. Eventually, finding through optimization the optimal protective measures. So let me go very, very briefly over this. What we're doing is we're doing simulations over, let's say, an 80-year period. This is 2020 to 2800. The threshold of 1.9 meters is the threshold above which there is damage in New York City. Up to 1.9 meters, there's not any major damage. And this is sea level rise that we're considering. And you see the simulations, and you see, I don't see the increase in the height of these storms. But if you do 1,000 of them and you put them together, you clearly see the sea level rise. So this is 1,000 simulations over this 80-year period. Once we have for each storm the maximum storm surge height, we can calculate the evolution of the height of the water, calculate the height of the water at every point in New York, calculate damage to the infrastructure above ground, calculate the flooding in the subway system, and then put together the entire losses for each event. I'm not going to go again. This is a methodology we have developed above and below. But these are, again, 1,000 simulations, 1,000 red curves, 1,000 warm season simulations, 1,000 blue curves. You see, cold season, and this is damage loss. Of course, it accumulates in time over 80 years, 2020 to 2100. In general, warm season damages are higher than cold season damages. You can plot their probability distributions. This is in the billion of dollars in the horizontal axis. And we have done a very preliminary, this is very important. We're not doing this in a vacuum. We have consulted with all these agencies in New York City. Port Authority of New York, New York and New Jersey has a lot of infrastructure. Metropolitan Transportation Authority in New York City is running the subway. Emergency Management Office, as well as the affected communities. We conducted interviews with the affected communities. And there is a study for Lower Manhattan. This is Lower Manhattan. This is very, very preliminary. One protective measure, a wall around the lower part of Manhattan. I'm going to give you only the results here. So if you have a budget of $500 million, this is the case, the best way to spend it is to build a wall from here to here. Again, this is Lower Manhattan, of a height that I cannot read from here. I think it might be 2 meters. This is the best use of $500 million budget. If the budget increases to $1 billion, you should build a wall here. If it increases to 1.5, this is the wall. If it increases now to $2 billion, you build a wall all around. But for this case, $500 million, it's better to build a wall of 2 meters high here, rather than, let's say, than building a wall all around at ½ meter high, if they have the same budget. So there is an optimization involved here. So let me close. We have developed this methodology that eventually establishes an optimal adaptation measure given a budget. And what we are working on right now is to extend this methodology beyond just storm surge and include rainfall-induced flooding. And then, of course, we can combine both and have storm surge and rainfall-induced flooding. But rainfall-induced flooding means that this can be adopted somewhere in Greece, where you have only rainfall-induced losses and damages. And how is this connecting with Greece and the Eastern Mediterranean in general? So this methodology, as developed right now, is only for sea level rise plus storm surge-induced flooding. we can have it, first of all, only for sea level rise. Sea level rise is critical for Greece. Greece depends on tourism, sandy beaches. Every unit of sea level rise, let's say you have 1 meter of sea level rise, you use 10 meters of your beach. Just think about this. Very, very major threat. Rainfall-induced flooding in non-coastal areas. You had the catastrophic floods in Volos and Pilion and Magnesia. And then, of course, all kinds of different combinations. And, for example, I'm wondering what would have happened in Athens if the catastrophic rainfall in Volos and Pilion occurred in Athens. What kind of flooding would have occurred in different parts of Athens? These are interesting questions to ask. And of course, heat waves, wildfires, desertification, these are other hazards that are threatening Greece and the Eastern Mediterranean in general. And of course, optimal solutions are critical as funds and budgets are always limited. This is acknowledgement of our support, and thank you very much.
Questions? Very nice presentation. I would like to ask, in order to implement these search process to identify the optimal measures, you have to be able to quantify the effect of these measures in the case of stores.
Absolutely, yeah.
And also to be able to quantify the cost of implementing of these measures.
Yeah. So in this very simple preliminary study in Manhattan, we consulted with some companies in New York City specializing in designing walls, protecting infrastructure from storm surges. So they gave us, first of all, the cost of building such walls in New York City. In New York City, you have to keep in mind, building anything is really extremely expensive. So we had this information, the cost per, let's say, 100 meters or kilometer of wall. And then our methodology was able, once we put a wall in part of the coastline of Manhattan, let's say over 3 kilometers with a certain height, to calculate what would be the reduction in damages in this part of the city. It is a methodology that we have developed that can calculate losses either without any protective measure or with, in the first simple study, just walls. But now we are studying the establishment of oyster reefs. A reef in general will reduce the incoming storm surge, and also introducing sealing individual components of the infrastructure. It is quite involved, the methodology, and it requires a lot of data that we were very fortunate to be able to collect in New York City over a long period of time.
You mentioned that it's very interesting what you said, that there would be an opportunity and a need, I would say, for Greece to apply this methodology in other areas. Like you mentioned floods, but rainfalling floods and wildfires. I think it would be very interesting.
Keep in mind, I don't have any expertise in fires, but I mentioned that it's an important threat.
Yes, you are right. That's what I wanted to mention, because it happened, I was Secretary General for Forests in Greece. So I know that it is very interesting, especially concerning wildfires and mega fires, to have such a methodology, I think this is something that could be of interest also for the ministry, to combine it also with the measures that we have to have in order to monitor certain areas against fire threat and risk, and also to know, to have let's say, an estimation of what would be the cost of fires, of mega fires in certain areas of Greece. I think this could be very interesting, because now we are talking about some billions of investment in this area, and maybe it could help to have this kind of methodology.
Look, from what I have read after the fires in California that were very devastating, as you all watched in the news, once such a fire starts and becomes large, is pretty much impossible to control. The only way, potential way out is in an area where you are expecting fires during a very windy time, very dry part of the season, to have drones that will be covering the entire area, and once a fire is detected, having again another group of drones carrying water and going there and extinguishing it within 10 minutes. I'm not saying that this is technologically feasible today, but there are people all over the world, I believe, that are working on some solution like this. Very quick identification and extinguishing it within 10-15 minutes. Once it goes beyond that point, in very, very strong winds, it's virtually impossible from our experience to extinguish it.
Yes, you are right, exactly. This is what we have been considering in the ministry. Smart forests, just to have sensors everywhere, and also
sensors, drones, yes, combination.
Yes, but where would you make this investment? In which area? What would be the priority? Maybe the methodology would be of using this.
This is the $1 billion, $1 trillion question globally, because you have a lot of different threats. Let's say in a country like Greece, you have rainfall, extreme rainfall events, you have wildfires, different parts of the country, you have earthquakes, of course. Somehow, you have to allocate a limited budget for prevention to the highest risk areas. So there must be a study that identifies different parts of the country as the highest risk. Let's say, I'm not, just out of my head, highest risk is I don't know, a major wildfire in Attica, or a major, I don't know, flood in Thessaloniki, or something else. But once using similar methodologies, because there are a lot of other people who have developed methodologies like the one I showed, and you are able to rank them, you might say, okay, let me try to use my limited budget for these 1, 2, 3. You make this public so that the population knows, okay, there has been an estimate of the relative risk. We have a limited budget, and we are going to use the budget for this area. So, I mean, at the end, population knows what is going on. These are some thoughts. I'm not claiming they are the 100% right approach. Something else might be even more effective.
On this question, so when this flood happened in the Volos and Thessalia, everybody was saying, why don't we have such studies, and what NTUA is also doing on that. So what would be the scale of such a project? How much would it cost?
First of all, let me say, there's no such study in the US, and I don't know any other European country that has such a study. So it doesn't mean that Greece is the only country that doesn't have a study. No country has such a study.
Now, I mean, we have global project.
Yeah.
Google Earth, we have a lot of computational power.
Mm-hmm.
I mean, there is no reason something that is done from New York, why not replicate it in even for the whole world, or at least for a country. I mean, France is doing a digital twin these days.
Even New York,
20 million or something.
even if New York establishes a full ranking of risks, the question is why spend the federal funds in New York and not in some other part of the country? California, Florida, Texas. Must be a global study of the entire country, because these are funds that probably have been collected by the government through taxes. They must be distributed in a fair way in the highest risk areas. And of course, highest risk areas have to account also for the areas that are inhabited by people with lower income, because these people are usually at a disadvantage. I mean, we don't go and spend federal money to protect an area that is inhabited by billionaires and they can repair their houses themselves. So there are a lot of parameters involved in this problem.
I would suggest that you discuss with
of course.
about the possibility of such a project in Greece. Yes, please.
Since you brought up the so at the beginning you said that you were preparing for Sandy, but not for the case where the tide is different, so that would have favored the northern part of the city. But then you did the whole analysis considering everything, and you still protect the lower.
No. Yeah, let me clarify. Look, that's a very easy part to misunderstood. We had the detailed data only for Manhattan below 34th Street. So we had information about every opening of the subway system, every station with every entrance. We didn't have this information for the rest of the city to do a study of the entire city. So this is the only reason that the results are below 34th Street.
Well, the question I wanted to ask, I mean, it seemed possible to me that if you did consider everything, it might still favor lower Manhattan because there's so much money there. I mean, if you do it by just economic losses, this is a very area full of economic assets. So do you ever try to recalibrate by, that people sometimes try to do instead of dollar losses, well-being, where you calibrate that a poor person...
Absolutely. This is an extremely important parameter, the income of the people living in different parts of the... But as I said, so far, the only other area we have started working is the area in Brooklyn close to Coney Island, because this is very low-lying, and it has also some very low-income areas there. Then we will be able to account for the income of the different communities.
So your metric is not just pure dollar loss, it's some human well-being.
Exactly. But because Lower Manhattan was quite uniform, we did not take it into account in Lower Manhattan.
Thank you very much. Last talk for today is by Christos.
Τέλεια. So, good evening from me. It's very hard to be the last speaker of a workshop, let alone be the speaker following Professor Deodatis. So I will try my best. Fortunately, I think quite a lot of my presentation is complementary to that of Professor Deodatis, so I will consider, I hope you were all paying attention to what he said, because I will consider it as a prerequisite to my work here. So what I will do, I will talk a bit more about this process of decision making, this creating of adaptation pathways, and quite a lot of the subject matter in terms of risks and critical infrastructures. I will So my name is Christos Makropoulos. School of Civil Engineering. I'm at the Department of Water Resources and Environmental Management. So indeed, if we want to get into questions about flood risk assessment in Greece, I would be happy to engage. There are a few more answers to the questions that we posed already. I'm quite fortunate to work with a very big team of very bright scientists. Quite a few water engineers, but also computer scientists, economists, environmental economists, and social scientists. And we work in this interface between water management, quite a lot of urban water management, and IT informatics, so creating the tools to deploy the solutions and the methods that we develop. And as part of this workshop, I sort of cherry-picked some of the work that we have been doing over the past few years. We have worked quite a lot on the data side of things, working together with the European Space Agency on Earth observation products that allow us to develop gridded precipitation products and align them with in situ measurements. We have worked on climate hotspotting. I'll talk a bit more about that within contexts of resilience. We have looked at emerging risks and how you can quantify them. We have done some work on soft sensing, looking at to augment, let's say, measurements on the ground with algorithmic processes that combine measurements that you have at different spaces and different scales to support our modeling work. We've done quite a lot of work actually on stochastic generation of hydrometeorological variables, so underpinning quite a lot of the work that was mentioned earlier on, and we've used it also to probabilistically model extremes, droughts and floods, and the repercussions of those on critical infrastructure, so for example dam breaks and things like that, but also flood risk assessment. Actually, we have worked in Thessaly and in Attica and other places. I'm happy to discuss that. Today I will talk more about adaptation pathways, so climate adaptation pathways and the ways we have attempted over the years to optimize the sequence of interventions in a rational way, so that risks like the ones we've been discussing all this afternoon could be reduced within hard constraints of times and budget. But we have also worked on the technology side, so we have developed new technologies for circular water management. Konstantinos knows quite a lot about this. We have developed this sewer mining technology, which is a very distributed wastewater reuse option for dense urban environments, and we've deployed it. There are quite a number of these units now deployed in Athens. We've worked on nature-based solutions and the way you can design and account for them at larger scales. We've worked on circular economy and industrial symbiosis. Again, Konstantinos and I have been working on this for quite some time, and indeed more alien things than what we've been discussing on critical infrastructure protection, especially the combination between the cyber and the physical layer of critical infrastructures and their interplays. And we've done some work on water distribution networks on that. I will only talk today about some of these, hopefully bringing them into a common narrative. And I will start, the issue of supporting decisions, of course, needs to start by asking decisions for what. That is obviously not a trivial question, as we have suggested already. As the quote goes, the trouble with today is that the future is not what it used to be. As Professor Moropoulou also mentioned, civil engineering infrastructures are especially tricky in this sense because they have these longer lifespans, these larger scales. They are highly interconnected. And the way we look for this preparing for what question is, of course, by looking at future states, and mostly in the literature we do scenario analysis. And there are, as you know, two major types of scenario analysis. One is the more probabilistic, the one that employs this stochastic generation of events that also Professor Deodatis mentioned, and the other is, of course, the more expert-driven scenario analysis, and each one is good for different things. The longer-term hydroclimatic series, but also the extreme events can better be captured with probabilistic models. Attributes that are more difficult to capture with modeling, perhaps with stochastic modeling, so political changes, geopolitical changes as things go, usually are expert-driven, but these are not, well, I would say satisfactory. Stationarity was mentioned as a problem with observations, historical observations informing future conditions, but also there's a very real constraint in expert imagination. I've worked for more than 10 years in the UK as part of work we did with an Imperial College for the UK government. We've done scenario work to death on all sorts of things. We have never ever mentioned Brexit in all my years there. Nobody had imagined it, and that really changed things. So it was years back now. So what we've been playing with recently is looking for more creative approaches to develop the scenarios, and we've turned to agents, LLM-based agents for different types of scenario creation, so that we can create these internally consistent narratives that we can use then to stress test our systems. So we do have quite a lot of alternative futures that we develop. Clearly, there is no possibility to, let's say, simply design for the worst case scenario. Professor Deodatis made this comment earlier on. You don't design for the worst case scenario. So this is where the thinking around resilience come into play. And for us in our work, resilience really is, well, we've developed a number of methods of how to, let's say, capture it in a more quantifiable way beyond the rhetoric. And this is some work that we've done a few years back now for the Dutch, interestingly, water sector, where we defined resilience. You can think of this as a stress-strain diagram. So the reliability or the performance metric of the system, so we have two systems here that we compare to each other, and this is their performance metric, say a reliability type of metric, and then progressively worse scenarios stress the system, and of course the system breaks as you push it and more. And what we are interested in is this remaining performance as the systems break. Every system breaks. We can't design systems that remain completely robust against all pressures. But the way they fail, the way a system fails matters because we can't protect them against everything. So resilience in this sense is really the area under the curve. And there are also very interesting other properties in this graph, but it's very intuitive, very easy. So then, looking within this resilience context against different futures, we thought, okay, perhaps we can also make planning more adaptive, decision-making about interventions and staged interventions more adaptive. And we looked into, this is actually recent work, only a couple of papers published in this over the past 6 months or so. We looked into reinforcement learning techniques, where we asked, let's say, the agent to solve these multi-stage optimization problems. Mostly we did this work on the distribution networks. It's not as trivial as it sounds, because it is not straightforward to define resilience and robustness the way I discussed it as a reward function for the agents. And indeed, what adaptive means for infrastructure planning is a bit vague. I'll try to answer at least on one occasion. So we've done this for water distribution systems. Actually, both this and the previous work are PhDs that are supported by European Research Council funds. Quite state of the art, I would say. We are getting very interesting results, trying to see how the agent develops the solutions, starting from, let's say, a limited set of solutions, and then branching out as the scenarios diverge, and then going back to see to what extent these decision points make sense from an engineering perspective, because by no means should we treat this type of solutions, smart agents and all, as black boxes. Rather the idea is to inform, let's say, or align this type of thinking with engineering judgment. So back to the real world, I'll take you to the region of Attica, and this is work we've done within a European project called Impetus. And Attica, well, we are standing within Attica. Our case study is East Attica in this particular case, and East Attica is a very rapidly changing part of the city. It's rapidly urbanizing still. Quite a lot of the environmental area, the remaining natural areas are being degraded. It hosts the Athens airport, 2 major ports, quite a lot of industrial activities, almost all of the industrial activities within the region are here. And as far as challenges are concerned, we've already mentioned forest fires. Konstantinos knows this all too well. Very recent, very devastating wildfires, but also something that we didn't mention today is that we are going through a drought period in Attica. Already 4 to 5 years of drought, persistent drought, have meant that our water resources are good for another couple of years, perhaps. Hopefully it will rain next year, but when engineers say hopefully it will rain, it doesn't really breed optimism. So indeed, there are very real challenges, and what we've tried to do in this work, of course, looking ahead into the future, which we do not know, we looked at ways to structure this speculation using what you all know as shared socioeconomic pathways. I will not go into them, but these come together with climate predictions, but also effects of these pathways, let's say, these narrative pathways on things like energy use, land use, and so on through EAMs, integrated assessment models. So we used some of the most standard ones, but then calibrated them with data from the region. And these are the projections for mean annual temperature for the whole region. So bold black line is historical data, projections from here on. Did the same for a number of variables. Precipitation, as you see, less clear of a trend, I would say. Projections suggest a minor decrease. To be fair, we've done quite a lot of work, Annie is also here, on precipitation over the country. We don't see a clear trend. I want to be clear about this. There is no clear trend on precipitation, nor extremes, as it were, but things are worse when it comes to, of course, the relationship between precipitation and evapotranspiration. And of course, we need to also examine demands. So the socioeconomic part, fortunately, we have been working together with the Water Company of Athens to forecast, well, not forecast, but analyze water demands for the city for the next decade. We are already seeing water demand rise in Athens for the first time in quite a few years. we believe this is linked to increased tourism. Attica has become a very important touristic destination in the context of Greece. So it used to be that people would pass through Athens and go to the islands. Attica in itself now is a destination of its own, an all year round destination. So we do see this in water demands. So it's not an ideal situation. There are some options, of course, to deal with such conditions. I'll be speaking about droughts in this particular case. Currently, as you may or may not know, there is a very big debate about new water resources development in the city of Athens. So these large-scale new water resource projects or ideas include very large desalination plants. There aren't any desalination plants in Athens, not yet. They also include large-scale water transfers. So there are ideas and plans for very large water transfers from the western Greece, and also reoperation of all the ground fields. So that is the supply side of the discussion. There's of course a demand side, a more circular, more local adaptation palette of options, which include wastewater reuse at various scales. There are both plans but also interventions on the ground, especially in Eastern Attica, where wastewater from the Eastern Attica wastewater treatment plants is treated at the correct level, let's say, so that it can be reused by agriculture and industry in that area. There are these smaller, more distributed units, which I call sewer mining. There are, of course, other nature-based solutions, as we talked before, demand management through controlled environmental agriculture. Interestingly enough, and although urban water demand, so managing urban water demand, decreasing per capita consumption always seems to be, it's on everybody's top list, let's say. In Athens, I would argue this will not mean much, because currently the average per capita consumption in Athens has dropped significantly. It's now around 100 liters per head per day, which is quite decent, I would say. But I would argue that tourism-oriented measures to manage these demands are still lacking, and for good reason, because they are so linked to the Greek economy. We can discuss it if you want. So what we've done in the project, we had this palette of options, we had the challenges, we did the projections, and we adopted this notion of adaptation pathways. So the idea is, of course, you never do all of the interventions at the same time or at the start. It costs money, takes time. Things change as you progress and you build things. Could we develop intervention pathways that are agile enough so that when things change and you are monitoring thresholds of particular critical indicators, so environmental indicators, you can switch to different parts of the path, a path that you have predefined, a path for which you know quite a lot, you have done your homework, as it were. May I suggest, and this is a parenthesis of course, that the big difference in well, sometimes how we do things here and the Dutch example that you gave is that they had done their homework, they didn't implement it until, of course, the event actually happened. But that's one thing. Starting to do your homework when the event actually happened is another. So if we are ahead in the curve, at least when things happen, we have something to move ahead with. So we've developed a set of tools and a method to implement such staged pathway approach, starting from a hotspot analysis, indicators, and cost effectiveness of interventions. By the way, the cost effectiveness part, so the costing part of the interventions, we didn't do ourselves. We had help from the Athens University of Economic and Business. And this is more or less the high level, let's say, sequence of activities in this adaptation pathway delineation. So system identification, the climate hazards, impact chain modeling, variable threshold. I'll explain what I mean by thresholds for variables. Then identify interventions, and then you do the pathway analysis where you include the regional data, and through essentially an optimization process, I'll explain what the objectives are here, try to sequence these climate interventions appropriately. I need to run. The part where we quantify the risks follows, of course, the usual exposure, vulnerability, and impact model. So we do have all the work. We have done quite a lot of that ourselves, but certainly not all. We do have the link between rainfall, temperature, the projections I mentioned, and the impacts in view of droughts of different types. We do have also the major, let's say, economic activities exposed from population, agriculture, industrial base, and we know their demands and the quality of water that they need. And then we have the, let's say, vulnerability elements, which include per capita consumption, whether we do or do not have central or decentralized systems, the state of the economy, and the state of the assets. Actually, as Professor Maropoulou said, the condition of the assets leave a lot to be desired. So as part of this work, and because the idea is that you need alerts, as it were, so that you can navigate through the pathway, we define, well, users define, in this case, this is a stakeholder-driven approach, so users define thresholds of least concern, medium risk, or medium concern, or high concern, or critical for different variables. So this would be hydroclimatic variables, but also investment or economy or GDP. In principle, you can do everything you want here. We define, well, we allow users to define relevant inputs, so weights, thresholds for different variables. And then we are able to start by plotting the risk as it evolves. It would be different based on the scenario that you select, of course. So these are combined risks from the narratives. You can actually, well, either identify particular risk, a drought risk, for example, or flood risk, and then generate pathways for that risk, or aggregate and produce more general, let's say, societal pathways. We've played a bit with both. And then, of course, the problem becomes what would be the best way or the best pathway that would be able to reduce this risk so that at some point in the future you keep it within an acceptable risk threshold. Now, all these words, best, acceptable, and so on, carry a lot of carry a lot of variables and subjective judgment behind them. So we looked at a number of, let's say, attributes of these intervention characteristics. We wanted, of course, and these actually, by the way, these attributes we didn't dream ourselves, we didn't do that in a vacuum, as was mentioned before. We collaborated with both the ministry and the prefecture and the city of Athens and other major stakeholders in the region. So we wanted to make sure that the effect on the specific vulnerability or exposure indicator was maximized. Costs were taken into account. Sorry, my apologies. Both CAPEX and OPEX costs. Feasibility actually plays a big role here, both in terms of TRL, but also in terms of societal readiness levels. And indeed, sequence implies precedent and antecedent solutions. So the degree to which the two or more interventions required each other or excluded each other had to also be taken account into the optimization problem, as well as, you know, the hard constraints of time to implementation, investment options, co-benefits, hidden risks, and so on. So quite a lot of characteristics or quite a lot of attributes and then we treated this as a multi-objective problem. We didn't do anything fancy in this case in terms of algorithms, so we just used an off-the-shelf GA for that. I'm sure there is quite a lot of room to improve it. We've done some work on evolving, on developing custom evolutionary algorithms ourselves, but not in this case. So the result is really a Pareto, where this is an example of a 2D Pareto, but in fact there are quite a number of criteria that you optimize for. This minimization of regional risks, the total cost of the pathway, the feasibility, deviations of annual spending. You can actually define an investment process or a type of investment that is available, and this could be different. It could be a big investment up front or a gradual investment, and you can take this into account because, of course, there will be other things that you can do in each case, hidden risks and so on. And then we plot the resulting residual risk. So the upper line is the baseline risk that is, let's say, the one that for the scenario we are trying to minimize, and the blue line is really the reduced after the specific solutions or the pathway that is selected. So I suggested some of the measures, the interventions that we've included in this portfolio of options that we wanted to sequence, including sewer mining, desalination, reuse, the information campaigns, and so on. So I'm cheating a bit because we had detailed studies ourselves of the effects of these interventions. So in principle, you can do it with any intervention, but these are the ones we could really quantify the effect on demand and reliability of the Athens water supply system. So then, I won't bore you with details, but generating all the solutions, we could see, looking at these alternatives, what the system selected, what were the types of interventions or solutions that it mostly gravitated to, and for what reason. Interestingly enough, it always included a significant proportion of sewer mining applications. Quite a lot of desal entered the mix, much less rainwater harvesting and the like. And actually, you could also, we also defined, identified, selected from the list and discussed with our stakeholders some of the more iconic pathways. So the ones that also made more sense from an archetypal point of view for decision makers. So there is the largest risk reduction pathway, the least cost one, the optimal trade-off between effectiveness and cost, the equal weights one, and so on. So these were part of the conversation with the stakeholders. And indeed, if you look into what the system came up with, then, and for sanity reasons, we did go back and see what was the, well, not rationale because this was a GA, but was there a sound engineering rationale for the selection of different measures for the different pathways? And you can see how, we could see how these options, these interventions were selected early or not in the pathway, depending on effectiveness, costs, trade-off, and so on. Just to preempt the question that was asked before, how does this relate to actual decision-making? It's interesting to see, and I think you made this point, it's interesting to see that when this discussion started, that was about a couple of years ago, when things were beginning to become stressful for Athens in terms of drought, there was a chaos. There was a more chaotic discussion, I wouldn't say chaos, more chaotic discussion. I see that the discussion is now being distilled towards some of the more identifiable parts of this more structured, let's say, formal decision-making, which is interesting. So we moved this much closer to, we are in the process of bundling this into software as we do, to make it much more accessible to policymakers and decision makers. So We are now developing a more homogeneous tool, which we call paths, and there are, I would say, beta alpha releases of that already, and this manages this process that I mentioned, allowing the user to input scenario data, identify the criteria for the pathways, run the optimization, and then select and query the pathways developed so that they can identify the types of solutions and discuss the type of solutions that I was presenting in a more human readable form. And this brings me to the end of my presentation, where asking the question, so what is still missing after all this and the presentations we had so far? I would say that despite our best efforts, and Dimitris made a very interesting presentation of multi-hazards and multi-infrastructures earlier on, we still, I think, have not really addressed the issue of multiple critical infrastructures and their cascades and interrelations. So between this very high level we discussed and the very, very local level, both of which are important, there is, I feel, an area missing where we are detailed enough to be meaningful, yet not at the very, very case-specific level. And there is, I think, quite a lot of work to be done, possibly in collaboration with our colleagues from Columbia. At NTUA, we have certainly taken a step, hopefully at the right direction, by creating an Institute for Critical Infrastructures. We call it the Institute for Smart, Sustainable and Resilient Infrastructures, and quite a lot of the colleagues around, well, this table, this virtual table, are members of this institute. Our purpose is really to work on this interface, develop multi-infrastructure, interconnected approach to assess, quantify, and manage these cascading risks across infrastructure. So I conveniently focused my presentation only on water infrastructure because this is closer to my heart, but in reality there is so much interconnectivity, more and more every day. We need to significantly improve our ability to anticipate not only the natural but also the technological risks and their cascades, what is being termed NATEC risks, but also find new ways in which we can assess, model and visualize these risks, not only again the physical but also the cyber and their combinations and the domino effects. Not only to learn and understand them, yes, of course, we are academics and would very much like to do that, but perhaps at some point also to develop a much more coordinated and more substantial resilience by design approach, and also co-develop with our stakeholders more realistic response and recovery plans for critical infrastructures. So thank you very much. To be continued.
This is fascinating work. I have a lot of questions that I would like to discuss with you. This is very, this is probably the ideal area to collaborate. But very quickly, you showed a lot of different criteria for optimization. Are you using one at a time? Are you using others for constraints? Because how is it possible to optimize at the same time? I counted 4, 5, 6, maybe more criteria.
So in this case, we have, it wasn't about really many criteria optimization. So we did optimize criteria 2 or 3 at a time. We used a multi-objective GA for that, so nothing revolutionary about it. Having said this, we have done explicit work on many criteria optimization, so around 10, mostly for water systems design. So there is, let's say, some knowledge of how to do it, but it becomes intractable for decision makers. Very quickly it becomes too difficult to, and this is why actually we found that this relatively simple stress-strain representation of resilience, although it hides quite a lot of things behind it, is intuitive enough at least to compare alternatives between them. And this, let's say, clarity is a benefit in talking to decision makers when they have to spend $500 million, as you said. Question.
So you showed in your optimization, you had like 181 Pareto optimal solutions, and then you translate that to a software where you hope others will be able to use it. So how, because this is a question I've been grappling with, is, and you kind of alluded to it, like what solutions do you decide to show in this interface where people could do their own optimization?
So the user is able to download all the data sets, and well, when you do have so many solutions, you need to decide which 2 or 3, because nobody can visualize or understand more than 3-dimensional graphs. So you can decide to visualize it any way you want. In any case, above 4 criteria, visualizing it at one go makes little sense. So in the interface, we select, or the user can select 2 or 3 to show, but you can download everything and do your additional analysis. At this point, the software is not, let's say, mature enough, I would say, so that it can handle everything within its own interface. So we do show some of these, and then the rest is left to I don't know, whatever software you use for big data analytics. Yeah.
Very impressive work. Very impressive. Thank you. Achievements. I think it's a comment that it's mostly directed to our students. They should realize that that's the beauty of engineering. Engineering is like problem solving. We are trying to solve problems often with the least amount of data, and this is actually the case here. I don't think we understand fully climate change. And we've seen from the previous presentations that we are trying to model it, to understand the evolution of this, to looking at the trends. Still, we are looking to find solutions. Even if we find solutions, we need to ask the right questions. Like, for example, we are doing with infrastructures to understand what's happening, how climate change affects our cities, our buildings, our environment, and so on. And the last session that we saw, Professor Deodatis and your impressive work, is that, okay, we have some solutions in mind. How do we prioritize them? So that's the whole picture of this. It's a complex problem. We don't know all the answers, but we need to give answers. We need to give them quickly before the climate change catches up whatever solution we have given. And that's, I think, the virtue of this workshop, that it brings together engineering and science, and from computer engineering to actual level, like civil engineering, like hard work and getting something structured. That's the move forward. We need to look bright ways to find clever solutions fast. So thank you for.
Fully agree. Fully agree. I think this is a great opportunity to talk, and actually it's a great opportunity to also talk to each other within the university. And I'm looking to the vice rectors for thanking them for that and asking for more opportunities for also NTUA staff to talk and collaborate. I'm sure we have, but of course with our colleagues as well. Thank you. Thank you.
The end of today's program, we had a lot of excellent talks. So the speakers have had dinner, right?